Welcome to this course on the dark side of the universe. Not the dark side of the force, we're not going to be talking about good and evil very much, but the part of the universe that we don't see directly, and nevertheless modern physicists and cosmologists have been able to piece together. The news that I want to get across to you over the next 24 lectures is that we have basically figured out what the universe is made of. This is an impressive accomplishment. This is only something that happens once in the history of the human race, that you figure out what the universe is made of, and it happened. It happened at the very end of the 20th century. At least we're pretty sure it happened. We have a picture that holds together very well, and we're going to be giving you the evidence for why we believe in that picture and what the other possibilities are. The other possibilities are even more dramatic than the idea that we got it right, so it's a no-lose proposition. Before going into any of the details, I want to give away the punchline right at the start. Explain what it is that we think we have figured out. And it's basically encapsulated in this pie chart. It's nice to know that all the secrets of the universe on the largest scales can be fit into one tiny little pie chart that reveals a lot. This pie chart is telling us the ingredients of which the universe is made, and the amount of slice that you have is how much of that stuff you have in the universe. That little yellow slice in the pie chart, 5% of the universe, is what we call ordinary matter. By this, physicists mean every single particle that we've ever detected directly in any experiment ever done anywhere on Earth, ever. So I'm made of ordinary matter, you're made of ordinary matter, this table is made of ordinary matter. Every star, every planet, every bit of gas and dust that we've ever seen is ordinary matter, the stuff that you see directly, and it's only 5% of the universe. 25% of the universe is the red part of the pie chart. It's what we call dark matter. It's matter, it's stuff, it's some kind of particles that move around, but it's dark. We don't see it directly. The rest of the universe, 70%, is something even more exotic than dark matter. It's called dark energy. The idea of dark energy is something that is smoothly spread out throughout the universe. So there's the same amount of dark energy here, as somewhere in the desolate cold of intergalactic space. 70% of the universe is this smoothly distributed kind of energy that we call dark energy. We know something about it. It's not that we know nothing, but it's a very interesting picture. So there's a lot to mention about this inventory that I'm claiming that we're having. On the one hand, when we call something dark matter and dark energy, it makes it sound like we don't know very much. What is this stuff? But that's not precisely true. I want to make it clear over the course of these lectures that we do know some things about the nature of dark matter and dark energy. There's things we don't know, and there are things that we know. The important part is that the dark matter and the dark energy are different than ordinary matter. It is not just that we've missed something, that there's some stars that we haven't seen yet, that there's some gas and dust that is spread smoothly throughout the universe, and this is really the dark matter. The truth is that all of the particles, all the ordinary stuff, all the stuff that is made of atoms and molecules is counted in that ordinary matter. The dark matter and the dark energy are something we haven't detected directly. We have evidence for believing that, and I'll tell you what it is. Of course, unless we are missing something, unless we're getting something wrong. So it is possible that the inferences that we use to go from observations of the universe to the existence of dark matter and dark energy have gone wrong somewhere along the way. It's not that we've made a mistake with the observations. Of course, if you make one observation, it's always possible you've made a mistake. But at this point, we're at a point where you've made observation after observation, you keep getting the same result. So there's something going on in the universe. It's not that we've made a mistake taking data, but we could be making a mistake in interpreting the data somehow. The way that we get from observations to the idea that there's dark matter and dark energy is to use the force of gravity. It's always possible there's something wrong with our understanding of the force of gravity, and we will be talking about that possibility. So one of the themes throughout these lectures is going to be what we know is true, what we believe pretty strongly is true, versus what we speculate might be true. We know that the universe is about 14 billion years old, if you count from the Big Bang to today. It's not worth talking about the possibility the universe is only 1 billion years old. We know better than that. We believe that 95% of the universe is a dark sector, 25% of it is dark matter, 70% is dark energy. We don't know that for absolutely sure because there are interesting alternatives, but that is the theory that fits the data by far the best. Then we start speculating about what is that stuff? What is the dark matter? What is the dark energy? Where do they come from? Why do they have the amounts that they do? Then we're into a regime where we're making hypotheses and we're going to be interested in figuring out which one of those is true, but we don't quite know yet. So over the next several lectures, we're going to be talking about how we got there, why we believe that 95% of the universe is in this dark sector, and then where we go next. What is going to be the kinds of ideas that we'll be approaching and the experimental techniques we're going to be using to get there. But first, let's step back. Let's put ourselves in context. What we're doing over the course of these lectures, talking about dark matter and dark energy, is participating in a kind of discussion that has been going on since ancient times. We're asking, what is the world made of at a fundamental level? The idea is that everything you see, whether it's me or you or this table or a star or a galaxy, can be reduced to a certain set of small components. And all the different kinds of things you see, the difference between me and this table, is that the small components that make them up are arranged in different ways. It didn't have to be that way. It could be that different things were just different. The stuff that makes up this table is just a completely different kind of stuff than makes up me or makes up the stars. But way back since the ancient Greeks, people have been wondering about the other possibility. Maybe there's only a small number of fundamental elementary constituents, and they get rearranged in different ways to make very different looking things. Now, if you were an ancient Greek, what you would say the elementary constituents are the elements: earth, air, fire, water. You would explain different substances that you saw by combining earth, air, fire, and water in different proportions and in different ways. Now that idea didn't fare very well. It didn't really become a scientific theory, but the important insight was there, that there's a small number of ingredients. All we do when we describe the world is take those ingredients, put them together in different combinations. That is still the kind of idea that we're pursuing in science today. It's been very successful, so we're going to talk about our modern conception of what those elementary constituents are. These days, it's not earth, air, fire, and water, it's elementary particles. We have a set of particles, a set of individual tiny dots that arrange together in different ways, that pull on each other using different kinds of forces, and make the stuff of which we are made. Now, it was Democritus, back in ancient Greece, who first proposed that the universe is made of indivisible particles, and he called them atoms. So an atom, to Democritus, was the tiniest little thing that you could make. If you took an object, you could divide it up into pieces and pieces and pieces, but there's a point at which you can't divide it anymore. There's the smallest possible piece, and Democritus called that an atom. So chemists in the 19th century took the elements of which we're made, carbon and iron and hydrogen and helium and so forth, and realized that there was in fact a smallest particle of which chemical elements were made. So they called these smallest particles atoms. Now these days we know that the atoms that we call atoms are not the truly elementary particles. They're not indivisible. You can actually divide atoms up. But it remains true that if you want to keep something being a chemical element, then it must be made of atoms. So we have an interesting way of characterizing all the atoms we see. We have the periodic table of the elements. We have different kinds of atoms arranged in different patterns, which give us different kinds of elements. And the chemists of the 19th century figured out how this was made, and you get, these days, over 100 different chemical elements. So that could have been the end of the story. That could be the universe in which we live. The chemical elements were the different elementary particles, and what we called atoms in the 19th century were in fact what Democritus was calling atoms. But that turns out not to be true. If you take an atom, these days we know we can smash atoms. We can take atoms apart, and what do we see? These days what we call an atom, we realize, is a nucleus, which is made of protons and neutrons. Protons are heavy, positively charged particles. Neutrons are heavy, neutral particles, joined together into an atomic nucleus. And around the atomic nucleus are spinning much smaller particles called electrons. The electrons are negatively charged. If you have the same number of electrons spinning around the nucleus as you have protons inside the nucleus, the total amount of charge in the atom will be zero. And a typical atom has zero net electrical charge. So we can take that atom, which is an electron or a set of electrons spinning around a nucleus, and we can divide it. We can say, move the electron over here, and we have a nucleus left. And then we can divide that. We can take the nucleus, we can divide it into protons and neutrons. So it is natural to ask, can we take protons and neutrons and divide them up into something even smaller? This is something that wasn't figured out until the 1960s and 1970s, but we now know that the answer is yes. Protons and neutrons are made of smaller elementary particles, which we call quarks. There's something called the up quark, which has a charge of plus 2/3. There's something called the down quark, which has a charge of minus 1/3. As we go later in lectures, we'll learn about all sorts of different elementary particles, and we'll realize that sometimes the names for them are very clever, sometimes they're very boring. So we have the up quarks plus 2/3, the down quark minus 1/3. A proton has 2 up quarks in it and 1 down quark. You can do the math, it comes out to a plus 1 charge. The neutron, on the other hand, has 2 down quarks and 1 up quark. It is neutral. So that is another layer of structure. You see the direction in which we're going. We go from atoms, which make chemical elements. We divide them into electrons and nuclei. Nuclei is the plural of nucleus. We take the nucleus and divide it into protons and neutrons. We take the protons and neutrons and divide them into quarks. It's very natural to ask at this point, what is next? What is the next layer? If we took an electron or a quark, could we divide those into smaller pieces? The answer is we don't know, but most of us believe that we can't. We actually think that electrons and quarks are part of the bottom layer of which ordinary matter is constructed. We'll go into the evidence for that a little bit later. But the key point here is ordinary matter. Out of up quarks, down quarks, and electrons, you can make everything you've ever seen. That's enough for all of chemistry, all of economics and psychology and literature and so forth. It's all up quarks, down quarks, and electrons. If we look out into the sky, we see stars, we see galaxies, we see gas and dust. Again, it's just quarks and electrons arranged in different combinations. We know that the quarks are there because we've done experiments at particle accelerators. We take heavy particles with high energies, zoom them towards each other at very high velocities. They smash into each other and they make more particles. That's how we discover new and new layers, but we think that the tiniest particles have now been discovered. The next question is, what are the heavier particles that we haven't yet discovered? We have a good reason for understanding why we haven't discovered heavy particles, namely that in that particle accelerator it takes more and more energy to make heavier and heavier particles. Einstein taught us that energy is mass times the speed of light squared. If you want to make a more massive particle, you need more energy in your particle accelerator, and that costs money. So there's a financial limit right now on how many heavy particles we can discover, but we're trying to push that more and more beyond. The question is, what other ways are there to discover new particles? We have a very nice picture of almost everything we've ever seen. We have, with quarks and electrons, the ability to put together atoms into molecules, into proteins, into desks and me and stars and gas and dust. But is it possible that there's other stuff out there that we haven't seen in the laboratory? How would we know? The answer is to look into the sky. The wonder that we're thinking here is that when you look at the sky, you see things, you see stars, you see galaxies, you see stars being formed. But is that what there mostly is in the universe? Are the things that you directly see the same things that the universe is really made of? The other possibility is that the things we really see are more like a decoration, that we are more like the olive in the martini of the universe. It's the part you see, but maybe not the important part for the whole concoction. So how would you know if there was stuff in the universe if you can't see it? By construction, we're saying that there's stuff there that we don't see. How are we ever supposed to figure out that it's there? Of course, I'm asking the question in a fairly leading way. It should be clear that it's very easy to become convinced that something exists even though you don't see it. For example, there's air here in this room. I'm convinced that it's here, even though I don't see it. I can see right through the air. Well, how do I know? How do I know for sure there is air in the room? There's many different ways I could demonstrate that. One way is just to wave my hand in the air, and I feel something reacting against my hand. The air exerts a force on my hand, even though I don't see it. We have other senses besides sight. We can feel the air in the room, even though it's invisible. Even though the air is dark in some sense, it doesn't emit light or absorb light, it's easy enough to tell that it's there. So how do we do the analogous thing to waving our hand, except we do it in the sky? The answer is we can't just put our hand into the sky and wave it around, but we can feel the force of gravity. Or more precisely, we can detect the influence of gravity on other celestial objects. So if there's some stuff out there in the universe, some stuff that exists and there's as much of it or even more of it than there is ordinary matter, that stuff will create a gravitational field. We can detect that gravitational field. That's what provides us the secret to detecting the dark side of the universe. So imagine, for example, if the moon were invisible and transparent. If you couldn't see the moon whatsoever, you could look in the sky with any kind of telescope you wanted, and you could never detect that it was there. Could we nevertheless be sure that there was such a thing as the moon? Could we weigh it? Could we figure out where it was? The answer is yes, because back here on Earth, we could observe the tides that occur in our oceans. Tides are due to the influence of the moon on the oceans here on Earth. In particular, the moon has a gravitational field, and that gravitational field pushes around the water in the oceans and the bays here on Earth, and you can therefore detect, just by looking at the waves and looking at the tides in the oceans, that there must be something out there exerting a gravitational field. You could even figure out where it was, and you could even weigh it. You could figure out how much gravity it had to be exerting. Fortunately, we can see the moon, so we don't have to do that, but you can do the same kind of process for other things in the universe. You can look out there in the universe, see the gravitational fields that are being created, and then attribute them to some kind of stuff, even if you can't see the stuff directly. So you see the possible loophole in this argument at the same time. In order to do this inference, you need to understand how gravity works. So even though we think that we do understand how gravity works, we'll take seriously the possibility that we're being tricked. We'll take seriously the possibility that something else is going on, that we don't understand gravity, and we'll try to ask whether it's possible there isn't any dark matter, whether there isn't any dark energy, but instead if we just don't understand gravity. The ultimate answer will be probably not. We think we do understand gravity. We think that there is dark matter and there is dark energy, but we need to keep every single possibility open until we're absolutely sure. The other thing we're trying to do, of course, is to go beyond looking at dark matter and dark energy through the gravitational field and detect them directly. So another possibility we'll be discussing is building experiments here on Earth that will produce dark matter particles, or that will wait until the dark matter particles come into the detector and bounce off of it, and therefore give us direct evidence that dark matter really exists. That may or may not be possible. That depends on properties of the dark matter, but we're going to try to do that. You never know what will happen. So let me just outline the entire rest of the course. I don't want to keep any surprises to the end. I want to give everything away. The picture that we're painting, in some sense, makes a lot of sense, but in another sense is surprising from some levels. It's better to hear the same story over and over again so it can really sink in so you understand what is going on. The first part of the course, lectures 2 through 6, will be about just looking at the universe. Actually going out there with a telescope, looking at what's in the sky, looking at galaxies, how they're distributed, where they came from, and so forth. And that's part of how you understand, that's certainly how you begin to understand what the universe is made of. But just looking doesn't get you very far, so at the same time, in those same lectures 2 through 6, we'll also be talking about the underlying framework that we use to understand the dynamics of the universe. That framework was given to us by Albert Einstein in the form of his general theory of relativity. General relativity, we'll talk about, is a theory of space and time and how it grows. So through the first couple of lectures, what we're going to be doing is going back and forth through looking at the universe, seeing what is out there, and then coming back here and thinking about it. When you think about what could be going on, and then you get a better idea for what should be going on, when you then go back to look, you can say, aha, I now understand something about the universe that I didn't understand before. What we'll see from looking at the universe and putting it in the context of Einstein's general relativity is that first, the universe is a pretty simple place. It looks more or less the same all over the place, except that it's getting bigger. The universe is expanding. It used to be smaller. In the future, it will be bigger. And that's an interesting fact that we need to think about. But the second thing is that the dynamics of the particles that we observe in the universe can't be explained only by those particles. In other words, what we're going to do is look at stuff in the universe from various different perspectives, radio telescopes, ordinary telescopes, individual galaxies, clusters of galaxies, the universe as a whole, put it together, and we're going to realize that it doesn't quite make sense all by itself. The only way to make sense of the dynamics of stuff in the universe in the context of Einstein's general theory of relativity is to imagine there is stuff there that we don't see. This is, of course, the stuff that we call dark matter. And we're going to see that if you imagine there is stuff in the universe that we don't see, then suddenly the dynamics of galaxies and clusters of galaxies begins to make sense to us. So that is telling us that there's something out there, something in the universe, that we haven't yet directly detected here on Earth. We have a very good view of the kinds of particles that exist in atoms, and they don't seem to be the same kinds of particles that exist out there that we are calling dark matter. So in lectures 7 and 8, we're going to take a step backwards, back here on Earth, and try to talk about the actual particles that we know and love, the particles in what we call the standard model of particle physics. We said that electrons plus up and down quarks are enough to make all the stuff that we're familiar with. Well, how do we know that? So in lecture 7, we're going to talk about what different kinds of particles there can be. There are boson particles, which basically pile up on top of each other and make forces. And there are fermion particles. Fermion particles take up space, and those make up matter. It's good that they take up space, because otherwise everything would just collapse in together. So these different kinds of particles are both necessary to making an interesting universe. Thankfully, they actually exist. Then in lecture 8, we're going to go into the specifics, given that we can have bosons and we can have fermions. What are the particles we actually have in the universe? What is the complete set that particle physicists have detected? And it's actually quite a nice picture that has been constructed. We've put together basically a mini periodic table of the elementary particles of nature. In that table, there are still mysteries. There are still things we don't understand about why these particles, why not those particles. But it's a very impressive accomplishment that is consistent with a tremendous amount of data. It's kind of depressing, actually, to be a particle physicist. You don't like it when your theory is consistent with all the data. You like it when there are puzzles that you can try to explain. So one project in particle physics is to push our knowledge into some region where the standard model of particle physics isn't good enough. Cosmologists have already done that. They've found dark matter, and one of the things we're going to be talking about is why we think that dark matter is not part of the standard model of particle physics. Then we have some knowledge of particles. We can move back in lectures 9, 10, and 11 and apply our knowledge of particle physics to the universe. In particular, we will apply it to the early universe. The very famously labeled first 3 minutes of the universe are a time when things were crunched together, much higher temperatures, much higher densities, and all of those particles that we've discovered in the standard model of particle physics were playing important roles in the very early universe. So we're going to take the universe we have today, we're going to run the movie backwards to when everything was packed closer together at high temperatures and high densities. We're going to use particle physics to predict what things should have been like, and then we're going to wind the movie forward again. We're going to start making predictions for what our current universe should be like, based on our predictions for what the past was like, given what we think particle physics is like. The remarkable thing is it's going to work. We're going to get the right answer. We're going to make predictions based on what was going on in the first few seconds of the universe's history, and those predictions are going to turn out to be correct. That means we understand something important about what was going on just a few seconds after the Big Bang. In particular, there's two phenomena that we will focus on during these lectures. One is Big Bang nucleosynthesis, and the other is the cosmic microwave background. Big Bang nucleosynthesis refers to the time in the universe's history when it was a nuclear reactor. It was taking individual protons and neutrons and fusing them together to make heavier elements. The specific detailed properties of what were going on when the universe was only a few minutes old come into making predictions for how much of each kind of element we should have. That's the kind of prediction we can make, and it turns out to be right. The cosmic microwave background is also describing a relic from the earliest times. It is the light that was emitted by the universe at the earliest times. When the universe was young enough, it was opaque. You couldn't see your hand in front of your face, imagining that you were there in the very early universe. But when it was about 400,000 years after the Big Bang, it became transparent. So suddenly the light that was emitted from the very earliest times in the universe could stream across the universe into our telescopes and be detected today. It's been stretched into the microwave regime, just like your microwave oven at home, and we observe that today as the cosmic microwave background. It turns out you can learn a lot about the universe by looking at what the cosmic microwave background looks like today, and we'll talk about that as well. Then finally in lecture 12, we get to talk about dark matter in some detail. We're going to talk about what could it be. We'll already have seen, just by looking at the universe and applying general relativity, that we need to imagine that dark matter exists. That is the only way we can make sense of what the universe is doing. So we're going to say, okay, the dark matter does exist. What is it? Well, there are different proposals within particle physics for what the dark matter could be. There are proposals that it could be ordinary stuff. It could be stars that are just crunched together. Or it could be black holes. We'll talk about those, but we will argue that that is not going to be the right answer. There isn't enough ordinary stuff in the universe to be the dark matter. Probably it is some new kind of particle. So then we're going to say, what could the new kind of particle be? The most popular candidate for what the new particle could be comes from something called supersymmetry. This is a new symmetry of nature that relates bosons, which I mentioned, to fermions, and predicts a whole bunch of new particles. One of those particles could very naturally be the dark matter, so particle physicists right now are very carefully looking for where that is in the universe and in their particle physics experiments. So we'll emphasize a lot the possibility of supersymmetry. It's the most popular candidate for what the dark matter could be, but there are other candidates as well, and we'll talk about them too. So then in lectures 14 and 15, we'll start talking about dark energy. Dark energy is not dark matter, it's something different. It's very interesting that this 95% of the universe, which is the dark sector, is split into two very different kinds of things. So what we mean when we say that is that in order to fit the data, we need to imagine that there are two different things out there in the dark sector. One is the dark matter, which is a bunch of particles, and they settle down pulling on each other under their mutual gravitational field. The other is the dark energy that is smooth, that does not clump together under gravity. It also does not go away as the universe expands. Ordinary matter, as the universe gets bigger and bigger, becomes less and less dense, but the dark energy somehow persists. So we'll talk about why we think that there is dark energy. It turns out that the universe, in recent times, has begun to accelerate. Not only is it expanding, but it's expanding faster and faster. This is not at all what we would have expected on the basis of a universe with just ordinary matter and radiation in it, even dark matter. The only way we can explain the acceleration is to imagine there's something that doesn't go away, something called dark energy. Then as a final consistency check, we're going to measure all of the stuff in the whole universe all at once. Just to make sure that we're not missing anything, we're going to use the entire universe as a scale to weigh how much stuff there is, and find that if we imagine a universe which is 5% ordinary matter, 25% dark matter, 70% dark energy, it all adds up to everything we see. That is the best evidence we have, as we'll discuss, for the idea that we haven't missed anything. That once we include dark matter and dark energy, we have a complete inventory of what is in the universe. So then, of course, we have to ask, what is this stuff? So in lectures 16 and 17 and 18, we'll discuss different possibilities for what the dark energy could be. It's something that's smooth, more or less the same everywhere. It's something that doesn't go away, so that gives us some clues, but we have different candidates for what it could be. None of these candidates, frankly, are very good. We're very much in the hypothesizing stage of doing science when it comes to dark energy, but I'll at least tell you some about what they are. Then in lecture 19, we'll take a step back and say, okay, we've inferred the existence of dark matter and dark energy by measuring their gravitational fields. What if we don't understand gravity? As I said before, the idea that there is dark matter and dark energy comes down to the fact that we need to invoke them to explain the motions of particles. But if gravity is different than we think, if Einstein was not right when he invented general relativity, maybe we could do away with dark matter or dark energy. So we'll talk about that possibility. In lecture 20, we're going to pause a little bit to look at inflation. Inflation is a hypothetical idea in the very early universe, but it's closely connected to the ideas of dark matter and dark energy. Number one, because the mechanism of inflation is almost exactly the same as the mechanism of dark energy, making the universe accelerate. And number two, because inflation makes some predictions which turn out to be coming right only if you believe in dark matter and dark energy. So we'll put those pieces of the puzzle together. Now lectures 21 and 22 are like dessert. We get a little treat for doing all this good work looking at data. We're going to start imagining beyond things we've actually observed. We're going to be talking about parts of the universe we have no access to, what some people call the multiverse, extra dimensions of space, and string theory, a hypothetical theory that weds together particle physics and gravity. String theory should have something to say about dark matter and dark energy, but our current state of knowledge of the theory just isn't good enough to say anything for sure. So what I'm going to talk about with string theory is what might be true. If string theory happens in a certain way, what could the implications be for dark matter and dark energy? But then to bring us back to Earth, in Lecture 23, we're going to talk about how are we going to test these ideas. All through the course, I'll be mentioning experiments and observations that have been done, and some of them that will be done in the future. But there's a whole bunch, a whole retinue of techniques that are going to be used to probe the universe on the smallest scales and the largest scales. So I want to give you an outline of what kinds of techniques are going to be used, not just the next year or two, but the next 10 years, the next 50 years, to learn more about dark matter and dark energy, as well as particle physics, string theory, and inflation. So then finally, in Lecture 24, we're going to talk about where have we gotten and where are we going to go from here. We've learned a lot, a universe for which we claim to have a complete inventory, but in some sense it doesn't quite match our expectations. This universe in which we're only 5% puts us into a tiny little corner of the universe. We could have designed a much simpler and more elegant set of ingredients for the universe, but they didn't turn out that way. So why is it like that rather than some other way? How do we put these ideas into the bigger context? And what can we learn? And why are we even thinking about these ideas? We're going to talk about in that last lecture. So next time, in Lecture 2, we're going to be very mundane. We're going to go outside on a clear night and we're going to look at the universe and talk about what we see. This lecture is going to be a fun one. We're going to go outside and we're going to look at the universe, virtually anyway. We're going to stay inside and look at your DVD, I hope. But we're going to take a look at what the universe looks like on the largest scales, and we're going to get good news. The universe looks pretty much the same everywhere. It's a dramatic, simplifying feature that our observable universe seems to have. So in fact, this lecture is going to cover a lot of ground. This would be a perfectly good course all by itself, this lecture. But the good news is there are pretty pictures involved. So it's going to be a picturesque view of what the universe is made of as far as what we can see. And then in later lectures, we're going to take the evidence from what we see and plug it into our theoretical notions to try to derive notions of what it actually is made of. So even though the universe looks the same everywhere, there is one thing that makes it not quite that simple, which is that it's getting bigger as a function of time. What that means is that different objects in the universe used to be closer together. In the future, they're going to be further away. So we're going to tell you the story of how this was discovered, and then in the next lecture, what it means in a deep down level. It's very often that you will hear people trying to explain to you the concept of the expanding universe by appealing to really bad analogies. So as a professional cosmologist, this gets my dander up a little bit when people use these analogies with the best of intentions to explain the idea of the expanding universe. For example, they will have a balloon, and they will take a balloon, and they will put little dots on it, and they will blow up the balloon. And as the balloon gets bigger, you see the dots moving away from each other, and they go, aha, the dots moving away from each other are just like galaxies moving away from each other in the expanding universe. And that's correct in a sense, but you have to admit that when you see the balloon expanding, there's an inside to the balloon and an outside to the balloon. But our universe is not like that. So the balloon analogy only works if you look at the dots on the balloon and then imagine there is no such thing as the inside or the outside of the balloon. It's possible to make that leap of imagination, but it's harder than just understanding what's going on in the first place. Similarly, the other analogy that is very famously used is raisin bread. You start with a lump of raisin bread dough with raisins inside, you put it in the oven, and the bread expands, as perhaps you know. The raisins move away from each other and people go, there you go, it's like the expanding universe. But again, you get a misconception from this analogy, and that's because the raisin bread has an edge, it has a crust. The raisin bread is also moving into something when it expands inside your oven. The universe, as far as we know, is all there is. When we say it's expanding, it's not getting bigger into some pre-existing space. What we mean is that the individual objects inside the universe are getting further apart. Now, how is that possible? How can you have the individual objects in the universe get further apart even though it's not expanding into anything? So that's going to be the next lecture where we explain how Einstein's theory of general relativity allows the space in between the objects to grow. Space-time itself is dynamical and can expand. So I'm not going to use any analogies whatsoever. I think the best way of understanding the expanding universe is to actually visualize the universe, the actual universe that we're in. Because once you start conceptualizing it as some object inside something else, you get the false impression. As far as we know, our universe is all there is. There might be something outside, but we don't need to appeal to anything outside to understand what's going on. So let's just think about the universe. Let's think of going outside, standing outside on a clear night where there are no clouds, and looking at the night sky. Furthermore, let's imagine that you have perfect vision. So what I mean is not only that you can see things that are very faint, and you can see things that are very small, you can also see in all the wavelengths of the electromagnetic spectrum. In other words, you can see visible light, you can see radio waves, you can see X-rays. I'm giving you perfect vision. You're standing outside, you're looking at the universe, and you're saying, what do I see? Well, there's some things that are obvious. You see the sun and the moon. They're fairly nearby as far as cosmology is concerned. You also see stars. You see stars and you see planets orbiting around the sun. These are all well and good, but the thing that I want to focus on, that we would see if we were standing outside on a clear night, is something called the Milky Way. The Milky Way is a band of what looks like a cloud, what looks like milky whiteness stretching from one edge of the horizon to the other edge, overhead. And if you were able to look closely enough at it, you would realize that this thing that looks like a cloud is in fact made of stars. The Milky Way is a huge collection of stars, and we can look at it better in the real world. We can have a satellite. So in fact, NASA's COBE satellite, which is short for Cosmic Background Explorer, took an image of the Milky Way. Here's an actual image of the Milky Way taken from a satellite. It looks like a galaxy. It looks like a picture of a galaxy that you would see taken by any other telescope. It looks like it's taken from the outside. But we really live inside the Milky Way. The trick is the Milky Way is a disk. So you imagine a disk of stars all orbiting around each other, and we're located near one edge. So when we look inside, we see the center of the Milky Way is a concentration of stars. You see less stars in other directions, very few in the opposite direction. We are embedded in a plate-shaped collection of stars, and that is called the Milky Way galaxy. The Milky Way has about 100 billion stars in it. You don't know the exact number. Some stars are too faint for us to see, but 100 billion is a good order of magnitude estimate. Any such collection of stars is called a galaxy. The important point here is that these stars are not fixed, sitting there in space. They're orbiting each other. So there's a pull due to gravity from one star to every other star, and this entire collection of 100 billion stars is orbiting under their mutual gravitational field. So you could ask, is that the whole universe? Would it be possible to imagine a universe in which you had the Milky Way, a collection of 100 billion stars, some planets inside and some clouds of gas and so forth, and nothing outside, emptiness stretching forever and ever? Well, it's a very plausible idea. It's certainly worth taking seriously if you didn't know any better. And 100 years ago, that was the leading understanding of what the universe was like. This was the so-called island universe idea, that we lived in the Milky Way. The Milky Way was a collection of stars orbiting around each other, but there wasn't anything else. There wasn't anything outside the Milky Way. However, astronomers did know there were different kinds of things inside the Milky Way. When we look at the sky with our perfect vision, we see not only stars, which are always points, no matter how much you zoom in on a star. There's no telescope on Earth that ever expands it to look like a disk. It always looks like a point. But there were other objects that were not stars that you could definitely see did have an extent. These were called nebulae, nebulae plural of nebula. These look like fuzzy little patches in your telescope or on your photographic plate. So 100 years ago, this was the hot topic in astrophysics. What are these fuzzy little patches called nebulae? Here's a picture of the Orion Nebula. This is a picture that they couldn't have 100 years ago. We have much better telescopes today. You see, it's a very colorful, very rich collection of gas and dust. In fact, we know today that the Orion Nebula is a star-forming region. It's a huge cloud of gas that is gradually collapsing under its mutual gravitational force, and it will splinter off eventually to form individual stars. So that is one kind of nebula that exists. The Orion Nebula is right here in the Milky Way. There are many, many other nebulae just like it here in the Milky Way. Here's another picture of a nebula. This is called the Andromeda Nebula. To a telescope, 100 years ago, the Andromeda Nebula looks like a fuzzy patch, just like the Orion Nebula looks like. All these different nebulae that you could see 100 years ago had different shapes and sizes, but they were all fuzzy little patches. We knew they weren't stars, but we didn't know what they were. The truth is that the Andromeda Nebula is actually the Andromeda Galaxy. The Andromeda Nebula is its own collection of 100 billion stars orbiting under their mutual gravitational attraction. In other words, the Andromeda Nebula is just like the Milky Way. It is not inside the Milky Way. It's a separate collection well outside the Milky Way. We do not live in an island universe. We live in a universe filled with galaxies just like ours. So how do we know that? This is something that was first figured out by Edwin Hubble, who was a remarkable figure in his own right. It took Hubble quite a while to find himself as an academic. He grew up more famed for his athletic prowess than anything else. He was a high school track champion. He played for the University of Chicago basketball team when they won the National Basketball Championship, which they're not likely to do ever again. He was a Rhodes Scholar, went to Oxford, and studied law for a while. Studied Spanish for a while, came back to the United States and actually worked as a high school basketball coach as well as a lawyer. Eventually he realized his true calling was astronomy, so he got a degree, a PhD, in astronomy, and he went to California. The reason he went to California was to go to the Mount Wilson Observatory, which at the time was the world's leading astronomical observatory. They had just built a huge new telescope, the 100-inch Hooker telescope. 100 inches refers to the diameter of the mirror that was used to collect light. So you had a large mirror collecting light. You could see distant stars and distant galaxies with a better perception than you ever had before. So what Hubble did was to look at things that look like nebulae, little fuzzy patches, and number one, he resolved them into individual stars. So not everywhere, not at the centers, but at the edges of these nebulae, you could see that it was not just gas and dust. There were individual stars there, and there were a lot of them. That was certainly suggestive that these were not, in fact, just clouds of gas here in our galaxy. They were individual collections all by themselves. But you still couldn't be sure. It could just be that there were a few stars, that they were still relatively close and inside our galaxy. How do you know how big the Andromeda Galaxy is? You can't count all of the 100 billion stars. The answer is that Hubble was able to measure the distance to the Andromeda Nebula. He was able to figure out that the distance between us and Andromeda was such that, given the stars he observed, there must be billions and billions, as Carl Sagan would say, stars in that nebula. So how do you do that? You use a technique called standard candles. This is a very simple idea. Imagine that you have some object, and it's a certain distance away from you, like a candle, and you can see that it has a certain brightness. Then someone takes that object and they move it twice as far away. If you're in a dark room and all you see is the object getting further away, once it's twice as far away, it will seem dimmer to you. In fact, if it's twice as far away, it will only have 1/4 the brightness. There's an inverse square law. So as something gets further and further away, it looks dimmer. That makes perfect sense to us. The problem is, if you don't know how bright it was to begin with, you can't figure out how far away it is. So the difference between a candle and a standard candle is a standard candle is something whose intrinsic brightness is known. If you know how bright the thing would be if it were a fixed distance from you, and you know how bright it appears to you, you can work out how far away it must be to make that distance and that brightness make sense. So one of the major projects in astrophysics and cosmology, 100 years ago and still today, is to find standard candles and measure distances to things. As you're standing outside just looking at stars in the universe, you see all these stars, but you have no idea off the top of your head how far away they are. So what you do is you build up something called the cosmic distance ladder, and the most important technique is the use of standard candles. For Hubble, the standard candles he used were something called Cepheid variable stars. This is a type of star that pulsates. It gets bigger and smaller, and the standard candleness is not absolute. So Cepheid variables are not all exactly the same brightness, but they also don't all have exactly the same period of oscillation. In 1908, Henrietta Leavitt, an astronomer at Harvard, although women were not allowed to be called astronomers at the time, but she was an astronomer and she was at Harvard, and she noticed one of the crucial discoveries in all of astronomy, which is that there is a relationship between how bright the Cepheid variable is and its period of pulsation. So even though you don't know just from the fact that it is a Cepheid variable how bright it is, if you measure its period, then suddenly you do know how bright it is. So Henrietta Leavitt calibrated this relationship. She taught us if you see a certain period, then it must be a certain brightness. Hubble went to his Hooker telescope, the 100-inch telescope at Mount Wilson, and he discovered Cepheid variable stars in the Andromeda Galaxy, as well as in other galaxies. And he noticed that these variable stars, given their periods, were much, much dimmer than the Cepheid variable stars in our galaxy. So he could work out how far away they were, and he realized that Andromeda was a galaxy all by itself, comparable in size to the Milky Way. In fact, we now know that we live in a local group of galaxies. The Milky Way is one of them, and the Andromeda Galaxy is the other big one, and we have many smaller galaxies that are satellites of these two. So Hubble established the first important fact about our universe, namely that it is big. In fact, we now know that in our observable universe there are about 100 billion galaxies that we can observe. That's a convenient number. In fact, 100 billion is basically the only number you need to remember in terms of how big the universe is. There are about 100 billion stars in a typical galaxy. There are about 100 billion galaxies in the observable universe. The age of the universe is about 14 billion years, but that works out to very close to 100 billion dog years if one ordinary human year is 7 dog years. So 100 billion is the scale of the universe using different units. Here is a picture from what is now known as the Hubble Space Telescope, named after Hubble, which is an orbiting satellite that was built by NASA. This particular picture is called the Hubble Ultra Deep Field. All they did was take the telescope, pointed at a blank direction in the sky, a direction where they didn't know anything was there, but they let it sit there and collect a large number of photons over a large period of time, and then, so to speak, they developed the image. What you see in this picture is a lot of galaxies. Almost every little dot in that picture is a galaxy all by itself, with literally billions of stars in it. So Edwin Hubble was the one to figure out that the universe is big, that not only do we have a galaxy with 100 billion stars, but that galaxy is not unique, it's one of 100 billion galaxies spread throughout the universe. So that's a nice picture of what the universe is made of. It's not an island. It's not just the Milky Way galaxy surrounded by nothingness. There's a collection of galaxies spread out. But don't get complacent, because the universe is not just staying there, it's getting bigger. This is the second important fact about the universe. After the fact that it's big, the second fact is that it's getting bigger, and this is also discovered by Hubble. He was not the first to get on to some idea like this. In fact, an astronomer called Vesto Slipher noticed that galaxies that he observed tended to be redshifted in the light that came from them. So what does that mean? When we have atoms giving off light, it is very frequently the case that the light it gives off in a certain kind of atom is always at the same frequency. The wavelength that you have of light will be determined by what kind of atom is giving it off. So if you look at an atom and it's giving off this light, you know what wavelength the light should have. But when he looked at distant galaxies, he noticed that all of the wavelengths of light that he was observing were stretched. We're going to go into this more detail later, but basically you go from a short wavelength blue photon, particle of light, to a longer wavelength red photon, and Slipher found that this was happening over and over again in the galaxies he observed. Now the phenomenon of a shift in the wavelength of light was well known. It's the Doppler effect. The Doppler effect is the thing that makes the pitch of noise change as an object goes by you. You start with something that is coming toward you, and it goes by, and a very high-pitched noise that you hear when it's coming toward you will convert to a low-pitched noise as it goes away. That's just because the waves of sound coming toward you are compressed, going away from you are elongated, are lengthened. So you get a blue shift when something's coming toward you, something is squeezed to shorter wavelengths. When something goes away from you, you get a red shift. So Slipher looked at all these galaxies. He said they're all redshifted. In other words, all of these galaxies seem to be moving away from us. So that's halfway to saying the universe is expanding. All the galaxies are moving away from us. But it's not quite all the way. It was Hubble who figured out the rest of the story, because it was Hubble who knew how to measure the distances to galaxies. So Hubble went, and with his collaborator Milton Humason, compared the distances to galaxies that he had measured to the redshifts that Slipher had measured, and he found a fascinating result, that the apparent velocity that the galaxy would have to have moving away from you to explain its redshift was strongly correlated with the distance. The correlation is that the further away an object is, the faster it's moving away from you. So that is what you need to be able to say the universe is expanding. So instead of a bunch of galaxies exploding away in some primeval explosion, if we imagine that the whole universe is just getting bigger, if the space in between all the galaxies is expanding, then you will see close-by galaxies move away gradually. Far-away galaxies will be zooming away from you at a huge speed because there's more space in between you to do the expanding. That was what Hubble discovered. He didn't call it that, though. This plot that you're looking at right now is Hubble's original plot of the data. He plotted the distance on the x-axis and the velocity on the y-axis, and it kind of looks like a noisy plot. It kind of looks like there's a scattering of points there, but Hubble was a genius. So he drew a straight line through it, and he turned out to be correct. The next plot is a much more modern version. It looks like the points are much more closely aligned with a straight line, which is true, but also the size over which you're now measuring distances and velocities has grown enormously. So you really do have very strong evidence that the universe is expanding. If you look at this plot and think about what it's telling you, you realize that even though the universe is expanding, even though all the galaxies are moving away from us, it is not that we are in the center of the universe. We see nearby galaxies moving away, further away galaxies moving away even faster. But if you were that middle galaxy, if you were the galaxy in between, you would see us moving away in one direction and the distant galaxy moving away in the other direction. In other words, in this collection, every galaxy sees every other galaxy moving away from it, and the further they are, the faster they're moving away. There's no special point to this. Every galaxy is moving away from every other galaxy. It's the whole universe that is expanding all at once. So Hubble had an equation, and I'm actually going to show you this equation. Occasionally during this course we will see equations. We're not going to use them. I just think it's important not just to mention that equations exist, but to actually look at them and show what they're saying. So here's an equation: velocity equals h times the distance. H is a constant, a number, which we now call Hubble's constant. So this equation is just telling us that the velocity of a distant galaxy is some number, some fixed number once and for all, times the distance to that galaxy. So the further away the galaxy is, the faster it's moving away. Now I said once and for all, and what I mean is, in our universe today, every galaxy obeys this law, but the Hubble constant is really better called the Hubble parameter, because it's telling you how fast the universe is expanding. In the past, the universe was expanding much more quickly. So what we call the Hubble constant was a much bigger number in the early universe. It turns out that measuring the actual value of the Hubble constant is much harder than you might think. It's been something that cosmologists and astronomers have been struggling with for decades, but we think that we finally pinned it down. Wendy Friedman of Carnegie Observatories and her collaborators have measured the value of the Hubble constant, and the answer they got is 72 kilometers per second per megaparsec. So what does that mean? Kilometers per second per megaparsec is telling you the Hubble constant converts from distances to velocities. So 72 kilometers per second per megaparsec means that one galaxy, 1 megaparsec away, will be seen to be moving 72 kilometers per second away from you. If it's 2 megaparsecs away, it'll be moving 144 kilometers per second away from you. So what is a megaparsec? A megaparsec is 1,000,000 parsecs. A parsec is about 3 light years. In other words, a parsec is about 30 trillion kilometers. It's a very big distance. A megaparsec is a typical distance to a fairly nearby galaxy. So this number, the Hubble constant, 72 kilometers per second per megaparsec, measured by Wendy Friedman in the 1990s, is basically setting the scale for the universe. It sets the time that it takes the universe to expand. It sets the distances to different galaxies. So the fact that we figured out what this number is a big step forward in our understanding of the scale and the size of the universe. Now that we know that distant galaxies have this relationship, the Hubble law, their apparent velocities that you observe are proportional to their distances, it becomes much easier to map out the universe. Measuring distances to galaxies is hard. You can't find Cepheid variables in very distant galaxies, they're just too far away. But measuring redshifts is easy. So we can use the redshifts, the velocity measurements, as a stand-in for distances. If you know that the bigger the velocity, the further something away is. So this plot is a picture of where galaxies are in the universe, created by a survey called the Sloan Digital Sky Survey. We live at the center of this picture, and you see two cones moving in either direction. That's just because there was a northern hemisphere survey and a southern hemisphere survey. It cost money to collect every one of these data points, so they didn't observe the whole sky, they just observed parts of it. Every one of those little dots, which are almost too small to be seen in this plot, represents an individual galaxy. This is hundreds of thousands of galaxies spread throughout the universe. So you see two important lessons. One is that the universe is basically the same everywhere. There's no dramatic difference between one side of the sky and the other, or from place to place in that universe. If you took a big sphere of space that was sufficiently big, megaparsecs across, and took the number of galaxies in that sphere, and then took another sphere just as big in a completely different part of the universe, you would get basically the same answer. This is the crucial simplifying feature that makes it possible to study our universe in a systematic way. It's more or less the same. The second feature is that it's not exactly the same. When you look closely at this image, you see there is structure there. There are little holes where there are almost no galaxies. There are concentrations where there are more galaxies. Those are clusters and superclusters of galaxies. The evolution of the universe at early times from being almost perfectly smooth to being the slightly non-smooth, lumpy distribution that you see in this picture is a fascinating story that cosmologists are just beginning to unravel right now. The universe is pretty smooth on large scales right now. In the past, it was even smoother, and so we're trying to understand how we got there from here. So that's the picture that we have of the universe. It's quite a nice picture, but it's also quite provocative. To put it into context, we'll say the basics again. The universe is big. That is to say, it's not just one compact collection of stars. It spreads out as far as we can see. It's getting bigger. The space in between galaxies is growing. That manifests itself as the idea that every galaxy you see appears to be moving away from us, and Hubble's law tells us that the further away it is, the faster it appears to be receding. It is smooth on large scales, so we can treat the universe locally in basically the same way that we treat the universe far away. The same average density, the same number of galaxies, the same basic properties of the universe should apply here as somewhere very far away. And then we can start thinking about what that means. If the universe is getting bigger now, that means that in the past it was smaller. We can imagine taking the current state of the universe and asking, what was it like? Where did we come from? So if things were smaller, they were denser, they were closer together, there were more things in every cubic light year or every cubic megaparsec. And if that keeps going, if you can extrapolate that back, then things became very densely packed. They're very hot. As things bump together, they heat up. And if you keep going, you get to the Big Bang. You get to a point where the density is infinitely large, where everything is on top of everything else. That would be a naive extrapolation from the fact that we're expanding now. Go backwards, and what do you find? You find that everything is on top of everything else. It's perfectly reasonable to say we shouldn't be so naive. There might be some change in the velocity of expansion. Change in the expansion rate. Maybe it started out not expanding. Maybe the universe was static and only slowly began to grow. So what we need is a theory. It's not enough to make the observations right now that the universe is expanding. We need a theoretical understanding of how it should expand in the presence of different kinds of stuff. So that theoretical understanding is given to us by Einstein's theory of general relativity. So general relativity was invented about 1915. The expansion of the universe was finally discovered by Hubble in 1929. So physicists had about 14 years to play around to try to figure out what should happen according to general relativity. And what they figured out will be the subject of the next lecture and the one after that, is that the expansion of the universe depends on what is inside. So, in other words, after this picture of what the universe is like, we're drawn back to the questions of dark matter and dark energy. We have claimed in the introduction lecture that 95% of the universe is dark matter and dark energy. Dark matter is some kind of particle that is heavy, massive, slowly moving. but has a local gravitational field. Dark energy, something that is smoothly spread out and something that persists. It doesn't go away as the universe expands. So given those ingredients, given the theoretical understanding of space and time that general relativity provides, we can ask the question, what did the universe look like in the past? Was there a Big Bang? What will happen to the universe in the future? Will it expand forever or will it contract? Now, these are not trivial questions. When Einstein invented general relativity, someone started saying very quickly thereafter that if space-time were expanding according to this theory, there should be something called the redshift. There should be a lengthening of the wavelength of photons. But not everyone believed it. Einstein himself was very skeptical about this effect. So when Hubble found that the universe was expanding, found that distant galaxies obeyed this relationship, they had a velocity that was proportional to their distance, he never spoke about that phenomenon in terms of general relativity. Hubble never said, I discovered the expansion of the universe that people working with general relativity had predicted. He always talked about just what he observed. He was a really good observer. He didn't want to make predictions or judgments on the basis of theories. So he never said, I've discovered the expansion of the universe. What he said was, I've discovered that distant galaxies are moving at a velocity that is proportional to their distance. He also kept saying, and I deserve the Nobel Prize for discovering this, but he never won the Nobel Prize. In Hubble's time, the Nobel Prize for Physics So this is perhaps my favorite lecture. Don't hold me to that. I might say that other lectures in the future are my favorite, but this is the one in which we take the expanding universe that we talked about last time and we ask, what does that really mean? We won't answer that question until the next lecture, but this question is going to take us into trying to understand how space and time work. And this is the real thing that made Einstein quite a famous international celebrity. He is the person who figured out how space and time work. And he figured out how they're related to gravity. So this is something in which Einstein did better than Isaac Newton did, which is a hard thing to do. So we're going to go from what Isaac Newton did up through Einstein, explaining along the way how we get there. And it really is a set of deep ideas about the structure of space and time that are counterintuitive. So we'll be thinking pretty hard about why things are like that and why they're one way rather than another. So let me start just by thinking about what the ideas of space and time are supposed to be. Space and time are what help you locate things. Space tells you where things are, and time tells you when things are. So let's think about space. To begin, scientists like to say that space is three-dimensional. What does that mean? That means that if you want to locate the position of an object, in principle, you need to give me three numbers. And the way that you can give me those three numbers can be different depending on the circumstances. So for example, the three numbers you give me might be the height of something, the length of something, and the breadth of something. Once you give me those three numbers, you've specified its dimensions entirely. If you only gave me two numbers, it wouldn't be enough. So we say that space is three-dimensional. Saying the same thing from a different way, if you want to meet somebody for coffee, you need to give me three numbers to say where to meet them. One way of thinking about that would be latitude and longitude and height above ground. Ordinarily, we're lucky enough to know the height above ground of the people we're going to meet, but you might tell them which of the two cross streets you're going to meet at. So it takes three pieces of information to locate something in the universe. That's what it means when we say that space is three-dimensional. Space is the arena in which things play out. Space is where you locate things, how two things come together, and how things are distributed all throughout the universe. Time, on the other hand, tells you when things happen. So say you're going to meet that friend of yours for coffee, and you give them the three numbers that say where you are going to meet them. That is not enough. You will not successfully meet them if you only give them those three numbers. You need to give them a fourth number, which is when you're going to meet them. So it takes four numbers to specify a unique point in the universe. The three numbers to tell you where you are in space, and the one number to tell you what time it is. You could think about all of these four numbers as being part of one four-dimensional thing called space-time. For a long time, people didn't think that way because there was no point. Space is something that is very clearly different than time. part of the revolution of relativity, as Einstein understood the universe, is to realize that space and time are in fact two different aspects of the same thing, a single four-dimensional thing that we call space-time. So what we're going to do in this lecture is start with Isaac Newton. Newton was probably without a doubt the greatest physicist who ever lived, and one of the things he did was to put together a very sensible picture of space and time. In Newton's picture of space and time are absolute. They're fixed structures of the universe. They are the stage in which the drama of physics plays itself out. Now, Einstein comes along, and he had collaborators also. He wasn't alone. In 1905, Einstein put the finishing touches on something called special relativity. Special relativity was a replacement for Newton's notions of space and time. Special relativity was the thing that first said that space and time are different aspects of the same four-dimensional thing called space-time. So in special relativity, there was still a fixed structure, but the thing that was fixed was one four-dimensional space-time, not separately the three dimensions of space and the one dimension of time. Then Einstein still thinks, he's not done yet, he tries to incorporate gravity into his theory of special relativity, and he realized that they're incompatible. He eventually throws away special relativity, replaces it with something better, which we call general relativity. General relativity is just as good as special relativity, but it also includes gravity. And the profound difference is that now nothing is fixed. Nothing is given to you ahead of time in general relativity. The very structure of space and time themselves are dynamical. They can change. Space-time has a geometry and a curvature, and it's that curvature that we interpret as gravity. So that was the short version of the story. Let's go slowly through the longer version. Here is a picture of Sir Isaac Newton. As I said, arguably the greatest physicist of all time, also arguably the greatest mathematician of all time. It was Newton who invented calculus, among other things, and among the pieces of physics he invented the fact that when you pass white light through a prism, it separates into colors. He invented the law of gravity that we know and love, the inverse squared law. The gravitational force between two objects goes down as they get further away, and as you double the distance, the force of gravity goes down by a factor of 4, the square of the factor of 2 that you double the distance by. So that inverse square law of gravity will play a very crucial role in what is to come, but it is not what we're going to be talking about in this lecture right now. What we care about today, right now, is what Newton said about space and time. So we think that space and time are so immediate and obvious there's almost nothing to say. That's where things happen. Space tells you how to locate things. Time tells you when things happen. What more do you need to know? But one of the great features of the Newtonian revolution in physics was being quantitative, attaching equations to things. It wasn't good enough to just say, well, space is where things happen. You need to have some equations, you need to have some mathematical structure. So Newton did that. Newton told us what it means to say that space is an absolute three-dimensional set of points, and that time is a different, absolute one-dimensional set of points. The basic picture of the Newtonian universe is shown here in this diagram. It's taking the four dimensions that you need to slice up the universe and slicing them up into moments of constant time. Sadly, on a two-dimensional picture, I cannot draw all four dimensions of space-time, so the two-dimensional planes that we've compressed diagonally in the picture are supposed to represent all three dimensions of space. So this picture should not be intimidating. It's a fairly straightforward representation of the universe according to Isaac Newton. We know better now, and we'll get to how we know better now, but this is how space-time worked according to Newton. There was space, and there was time. So what you see here is little clocks. Each clock tells a different time located on a different moment of space. So the Newtonian universe is one where space happens over and over again. It happens at different moments in time, and at every moment, objects are going to be located in slightly different places. And so we call that motion through space. Things change as a function of time. And that's how Isaac Newton's universe worked. So the point that I'm emphasizing about Newtonian space-time is that it is fixed and it is absolute. So what does that mean? Those are two different words. Fixed means it never changes. There's the structure that space and time are staying there. They don't change into something else. The rate at which time flows does not depend on where you are. there's one fixed thing called the flow of time, and it's the same all throughout the universe. That's what fixed means. Absolute means it's the same for everybody. The rate at which time flows, or the distance between two objects, doesn't depend on who you are. It doesn't depend on where you are, on how you're moving through space. It's just a notion. There's a notion of it took 3 seconds between this event and that event. Everyone agrees on the fact that it takes 3 seconds between these two events, no matter where they are, no matter how they're looking at it, so long as they take accurate observations. These will change, these notions, once we get to relativity. Absolute, in the Newtonian sense, is opposed to relative. So the absolute fact that a certain object has a certain length is going to turn to a relative fact in relativity. What that means is that the length of an object will depend on who is measuring it, depends possibly on where they are, certainly on how fast they're moving. Fixed is what we'll get rid of when we go from special relativity to general relativity. In general relativity, space-time is dynamical. It can change and it can take on different forms, and it will no longer be absolutely fixed. So to understand the change from Isaac Newton's absolute space and time to Albert Einstein's relative notion of space and time, we have to understand how you would go about operationally making sense of Newtonian space-time. In other words, it's one thing for me to say, yes, there are moments of time that are the whole three-dimensional universe of space, and those three-dimensional spaces repeat themselves over and over again. But what does that mean? How do you make sense of it? The way you make sense of it is doing something that you see in spy movies all the time. You synchronize your watches. So when I say that there's a moment of time that extends throughout the universe, what that means is I have a clock right here, it says a certain time, and I can set up clocks all throughout space that agree with this clock. So when this clock says it's 3 o'clock, it is 3 o'clock here and everywhere else. These are just a set of words. How do I make them real? What I do is, first, I set clocks throughout all the universe. That's the easy part. We're doing thought experiments here. These are not real experiments. We have a clock sitting at every point in space. But we have to synchronize our clocks. So we take the clock that we have here, we take for granted that we have good clocks. These are clocks that run at the same rate. They are reliable clocks. So we take the clock we have here, we leave it here, but we take another clock and we set it to say the same thing as our first clock, and then that second clock that agrees with the first one, we move throughout the universe. We move this clock, as shown in the picture right here, we move it to all of the other clocks, and when we get to another clock, we align them so they're reading the same time. By that procedure, we synchronize our clocks all throughout the universe. It doesn't matter what the clocks are doing. It doesn't matter how they're moving. It doesn't matter where they are. When we do this, when we take our one clock and we make sure that every other clock all throughout the universe agrees with it, we're done. We've synchronized our watches, as it were, all throughout the universe. That's what Isaac Newton says happens. There's only one rule in Newton's universe, which is that you have to move forward in time. In other words, if it's 3 o'clock here, then when my watch goes 1 hour to the future, I will be at 4 o'clock no matter where I am in the universe, no matter what I've done in the meantime. Then Einstein and his friends came along in the early 20th century and says, actually, it's not like that. We need to replace the absolute notions of space and time that Newton had by relative notions of space and time. In particular, the fundamental insight of Einstein can be summed up in the phrase, time is like space. So what is that supposed to mean? Suppose that you measure the distance between 2 points. You have a path that goes from one place to another. Well, you have to actually go down that path and measure the distance along the path. The distance could be different depending on the path you take. Einstein says that time is like that the rate at which time flows depends on what you do. This is really hard to get through your brains because it's very non-Newtonian. In some sense, even though Newtonian mechanics is a great triumph of the human imagination, it's still quite intuitive. It makes sense to us once we understand it. Relativity is very counterintuitive. Einstein says that the amount of time that you feel elapsing is personal. It's not a fact of the universe, it's a fact of what you do. It can be different for two different observers, even if they start and end at the same point. So let's see how that works. Imagine that you do in Einstein's universe, that is to say in the universe in which we actually live, what you try to do in Newton's universe. You try to synchronize your clocks all throughout space. So you take the clock that you leave here, it's reading a certain time, you take your movable clock and you make them agree, then you send out your movable clock to synchronize all the other clocks all throughout space. You think you've done it, but then you bring your clock back to where it started, and you notice that the two clocks don't say the same time anymore. It's not true that this clock, even though it's a perfectly good clock, clicked at the same rate as it traveled throughout space, synchronizing all the other ones. In fact, it turns out that in special relativity, there is no way to make that happen. You didn't make a mistake. It's just a feature of space and time that when a clock moves around, it measures a different amount of time than a clock that stays still. This seems weird to us because to make the effect obvious, you need to move close to the speed of light. The speed of light is the magical velocity in the theory of relativity at which all of these weird things become obvious. Since we're always in our everyday lives moving slower than the speed of light, we don't notice them. We think it's very strange for someone to say the amount of time that clicks off on my wristwatch depends how I walk, depends on the journey I take through space and time. But once Einstein tells us that time is kind of like space, there's a way of thinking about it that makes perfect sense. So in this picture, we're drawing an analogy between distances and times, because Einstein says that the two things work the same way. You draw two different curves that connect 2 points in space. One curve is a straight line, and one is sort of a curvy thing that goes back and forth. Nobody in the world is surprised at the fact that the length along those two curves is different, even though they begin and end at the same point. Why should they be the same? They move in different ways. So Einstein says time works in the same way. Take 2 points in space-time. Take two events, 2 points where you're both located in space and time. Two people begin at the same point and they end at the same point, but they take different journeys. One just sits there, not moving, and one zips around. In space, it was the case that the shortest distance between 2 points was a straight line. Any curvy path you went along gave you a longer distance. Einstein says that a very similar thing happens with one interesting twist. Einstein says that the longest time that elapses between two moments is if you just sat there and waited for time to go by you. If you zip off and come back, you will have experienced less time than your friend who stayed behind. The shorter time is the path through space-time that zips around. There had to be some difference because we know that time is not exactly like space, but Einstein is telling us that deep down, space and time work in similar ways. Just like the distance along a path can depend on how you move, the time that elapses on your wristwatches depends on how you move through space-time. So that's the fundamental difference between space-time in Einstein's universe and space-time in Newton's universe. But remember, there was one rule in Newton's universe. You had to move forward in time. That rule gets replaced in special relativity. And in fact, the rule that you have in special relativity is more stringent than the one that had in Newton's universe. In Newton's universe, you could move as fast as you wanted as long as you kept moving forward in time. In Einstein's universe, the speed of light is special. So if there's an event in space-time and you want to get somewhere else in space-time, you can only plausibly get there if you move slower than the speed of light. So if you imagine drawing a picture of space-time, and you have an event and you imagine all the light rays that are leaving that event, those light rays represent the ultimate speed limit. They represent the velocity faster than which you cannot travel. So there is no allowed trajectory through space and time that moves faster than the speed of light. Everything you're allowed to do moves up in that diagram. It eats up more time than space, if you like. So that is the fundamental rule in special relativity. Newton's rule is you have to move forward in time. Einstein's rule is you have to move slower than the speed of light. That set of things, faster than which you cannot go, is called a light cone, the set of all points connected to your original event by things moving at the speed of light. So the only thing you need to remember is, whatever the speed of light is, where you are in the universe, you need to move more slowly than that. That is the fundamental rule. So this was a replacement, as we mentioned, for Newton's concept of space and time. Newton was the greatest physicist who had ever lived. He invented not only this notion of space and time, but also the theory of gravity and many other things. So Einstein knew that if he's going to replace Newtonian space and time, he would have to reproduce the other successes that Newton had. Newton had a very good theory of how gravity worked. He was able to predict how planets moved around the sun or how the moon moved around the earth. This theory of Newton's was verified to high accuracy over and over again by experiments. And here comes Einstein saying it's not right. So clearly you have to reconcile the new theory of space-time, special relativity, with what Newton thought gravity was. Gravity was the inverse square law. The force due to gravity is proportional to the mass of the thing that is pulling you, and inversely proportional to the distance squared between the objects. So after inventing special relativity in 1905, Einstein devoted himself to this task of trying to figure out how to reconcile gravity with his new notion of space-time. It took him 10 years to do it, and the way he ultimately did it was to realize just you needed to throw away what Newton had told you about gravity. The way that gravity was going to work in relativity is just very different than it works in Newtonian mechanics. So here's a picture of Einstein. You've all seen pictures of Einstein before, but usually when you see pictures of Einstein, he's in his older ages where he has let himself go a little bit. He had the hair going up like that, and he was wearing a sweatshirt, and he wore the same sweatshirt for days and days. This is a picture from 1912 when Einstein was young, a sharp-dressed man, and somebody was combing his hair, and he was thinking about the nature of space and time and how to make it compatible with gravity. Ultimately, he hit on a thought experiment that provided the key to understanding how gravity would work in the context of relativity. And the thought experiment actually traces itself back to Galileo. Galileo, the famous Italian physicist who lived just before Newton, who really invented a lot of the framework that Newton made sharp and quantitative and attached equations to. Galileo was one of the best physicists of all time. One of the many, many things that he did was to understand that gravity is universal. The famous experiment that he may or may not have done, probably not, but it's a nice visual image, is to drop objects off of the Leaning Tower of Pisa and notice that no matter what the objects are made of, no matter what the mass of the objects is, they always fall at the same rate. In other words, gravity as a force has a very strange characteristic, that everything responds to it in the same way. So that's different, for example, than the force of electricity. The electromagnetic force has the property that there are things called positive charges and things called negative charges. They move in different ways, in opposite directions, in an electric field. But gravity, everything moves the same way. Gravity has this feature of universality. Everything responds to it identically. So Einstein, because he's smarter than you or me, realized that this was the key to understanding how gravity works, the fact that it works the same on everything. What that meant is that gravity is undetectable. That's a bit of a surprise to say that gravity is undetectable. It seems kind of obvious that if I let something fall, I see the force of gravity at work. But what Einstein says was, imagine that you're in a box. You can't see outside. Someone asks you the question, is there gravity in that box, in that room? Well, you can drop things, you can see them fall, and you go, yes, I have seen gravity. But Einstein says you might be very far away from any gravitational field. It might be that you're in a rocket, that you're being accelerated at a tremendous rate through interstellar space where there's no gravity around. In that rocket, if you drop things, they will fall in exactly the same way that they would fall if there were gravity. This is not true for electricity. You can detect an electric field because you drop a positive particle and a negative particle, they move in different ways. But because everything moves the same way under the influence of gravity, you can never be sure, if you're in a small region of space-time in a tiny little box, that there is any gravity. So again, to you and me, we say, well, that's interesting. To Einstein, he says, that's the key. If everything responds to gravity in the same way, then gravity is not a force at all. Gravity is a feature of space-time itself. In fact, the feature it is the curvature of space-time. Einstein's most brilliant insight was to say that space-time has a geometry. And in 1915, he came up with general relativity, which was to describe how the geometry of space-time, how the curvature of space and time itself, manifests itself as what you and I observe as gravity. So according to Einstein, we have a picture something like this, although this is a somewhat colorful conception of what is going on. We have the sun that is warping the space around it. The usual analogy that is used here that is pretty good is that you put a bowling ball in a rubber sheet, it distorts the shape of the rubber sheet around it. And a marble that you rolled by that bowling ball would be deflected by the curvature of the rubber sheet. What Einstein is saying is that that is what is happening in space-time. That is what gravity really is. The gravitational force that we attach to the sun is really the warping of the geometry of space near the sun. What the Earth is doing is the Earth is just doing its best to move in a straight line. But there are no straight lines because the geometry itself is curved. So what we see the Earth do is to orbit the sun. The orbiting of the Earth around the sun is just the Earth's response to the geometry of space and time. This was Einstein's brilliant idea. Now again, it's not enough to just say words like that. You need to make it quantitative. So Einstein has an equation known as Einstein's equation. Einstein's equation is not E equals mc squared. That is a very good equation, and it is Einstein's. It's very famous, and we'll talk about that more later. But what is known to physicists as Einstein's equation is the equation for gravity. And I'm going to show it to you here, again, not because we're going to understand this equation in any great detail, but it's nice to see just what it looks like. You should get an appreciation for the art and the poetry that are these physicists' equation. This is Einstein's equation, and what it is a left-hand side and a right-hand side. So that part is easy. The left-hand side is describing the way in which space-time is curved. It's a set of numbers. In fact, it's a 4x4 matrix, a little array of 16 numbers, and the values of those numbers are telling you by how much space-time is curved. If space-time is flat, if it's like this tabletop, if there's no geometry, all those numbers will be 0. On the right-hand side, you have stuff. So you have 8, pi, and g. These are just constants of nature. They're just fixed numbers. And then you have the energy and momentum of the stuff in the universe. Anything that is in the universe comes along with energy, comes along with some substance and some heat and some pressure and things like that. And what Einstein is telling you in very specific equations is that all of those things contribute to the curvature of space-time. What Newton would have told you is that what makes gravity is mass. What Einstein is telling you is that what makes gravity is everything. Every form of energy, which includes mass, but also includes heat and pressure and temperature and stress, these all contribute to gravity in some way. So this equation, Einstein's equation, is the one that should be famous. It's a little bit more intimidating than E equals mc squared, a little bit less immediately relevant to our lives, but it's a tremendous accomplishment to conceptualize gravity as a feature of space-time itself, as a feature of the curvature of space and time. So you're allowed to ask, who cares? Why should it matter that I use the words gravity is the curvature of space and time rather than gravity is a force stretching through space and time? Is there any difference between these two sets of ideas? Well, there are differences, and the differences are going to make a big difference to us in our quest to understand cosmology, dark matter, and dark energy. The first implication of the claim that gravity is the curvature of space-time is that universality, the fact that everything responds to gravity in the same way, implies as its converse that everything creates gravity in the same way. There's a universal coupling between the curvature of space and time and the stuff in the universe. In other words, you can't hide from gravity. If there is stuff in the universe, if it has mass and energy, if it exists in any substantial physical way, it will give rise to a gravitational field. So Einstein is giving us a surefire technique for detecting absolutely everything in the universe. There is nothing that can hide from us as long as we can detect gravitational fields throughout the cosmos. You can't hide from gravity, so you can go the other way. By detecting gravity, you can infer that there must be stuff. If you see a gravitational field pointing in some direction, there must be some stuff there causing that gravitational field, even if you don't see the stuff. This will be the technique that we use to infer the existence of dark matter and dark energy. Dark matter, we will say, must be there because we will see stuff being pulled in some direction where there's not enough ordinary stuff to explain it. Dark energy has a more subtle effect. It makes the universe accelerate. And we'll talk about how the acceleration of the universe is a manifestation of the curvature of space-time in the way that would be caused by dark energy. The second implication of the motto that gravity is the curvature of space-time is that space-time is dynamical. Space-time can change as a function of time. It need not be the same in the past as in the future. So it gives us a changed viewpoint on how we would think about the fact that galaxies, for example, are moving away from us. Hubble said that we have a velocity to galaxies, and the velocity is larger if the galaxies are further away. The same phenomenon makes sense according to Einstein, but we attach slightly different words to it, which is why when I'm being careful, I refer to the apparent velocity of distant galaxies, not the actual velocity. In the real, careful way of understanding things, a la Einstein, the galaxies aren't moving. The galaxies are sitting there, located in space, and what's happening is space is expanding. Space-time itself is dynamical, it can change, and what is happening is not that the galaxies have a velocity through space, but that the space in between the galaxies is growing, it's stretching, it's getting bigger. More and more space is coming into existence. This is a way of thinking about things that Einstein gives us that allows us to ask questions that wouldn't have made sense to Isaac Newton. We can say, for example, where did space and time come from? What happened at the beginning? Did space and time get created? Was there something before what we now think of as the Big Bang? To Newton, with an absolute fixed space-time, this kind of question doesn't really make sense. You don't ask where space-time came from for Isaac Newton. It was always there. With general relativity, saying that space and time are dynamical and can change, you're at least allowed to ask the question, why are they here? How do they come into existence? You will not be surprised to hear that we don't yet know the answers to these questions, but we're hoping in this lecture, we get to put together the picture that we've developed in the previous two lectures. So in lecture 2, we talked about what the universe looks like. If you stand outside on a clear night and look outside with perfect vision, what do you see? What we found is that what you see is a set of galaxies like our own. Every galaxy has something like 100 billion stars in it. There's something like 100 billion galaxies scattered throughout the universe. The good news is that they're scattered uniformly. There's the same density of galaxies all over the place. The more interesting news is that everything is expanding. So the universe is smooth, pretty much the same everywhere, and it's expanding, it's getting bigger. The galaxies are redshifted. Their light that is coming towards us leaves the galaxies at a certain wavelength, and when we receive it, the wavelength is longer, just as if those galaxies are moving away. In the third lecture, in the previous one to this one, we discussed Einstein's theories of special relativity and general relativity, his theories of space and time. In particular, general relativity was the lesson that what we perceive as gravity is a manifestation of the curvature of space and time. Space and time are combined together in something called space-time, and that one four-dimensional space-time is dynamical. It can stretch and move, and the results of those stretching are what we perceive as gravity. So what we want to do in this lecture is take the idea of a smooth, expanding universe, a universe that is the same everywhere throughout space but growing as a function of time, and understand it in the context of general relativity. What does Einstein's equation, what does the relationship between stuff in the universe and the curvature of space-time have to say about the idea of a smooth, expanding universe? So one thing that we mentioned, and it's worth emphasizing again, is that the fact that the light from distant galaxies is redshifted when it gets to us is not, strictly speaking, a Doppler shift. The Doppler shift is what happens when you have two objects with a relative velocity. One object is moving toward the other one, and when it emits something, whether it's a sound wave or a light wave, that something has its wavelength squeezed, and you observe it as a shorter wavelength thing, either a higher frequency sound or a bluer ray of light. If it's moving away from you, the wavelength would be stretched. That's the Doppler effect. A very similar thing happens according to general relativity, but it's not the Doppler effect. It's not that this thing is moving toward you or away from you. It's that the space itself is expanding in between. That is the origin of the cosmological redshift. It's that the space-time itself is dynamical. So the amount of space is getting bigger, and we're going to try to understand that in a slightly more quantitative way. So talking about quantitative ways, we'd like to ask, how big is the universe? Is that a question that makes sense? And the answer is we don't know. we don't know both how big the universe is or whether the question makes sense. What we know is that we don't see any boundary to the universe. Because in Einstein's universe, space and time are dynamical, we can imagine different shapes that space could take. In Newton's universe, it was kind of obvious that if you went out in space, it would just go on forever and ever. Space just extended in infinite directions. On the other hand, in Einstein's universe, things can be curved. If things can be curved, they can be curved in on themselves. So we could certainly imagine a finite universe, a universe that had the shape of a sphere, for example. But what we see when we look out into the universe is we do not see the back of our heads. We do not see any evidence directly that the universe that we observe is finite in size. So that doesn't mean that it's not finite in size. It's just that we don't see any wrapping around or any edge to the universe. But it's not a complete surprise. We only see a finite part of whatever universe there is. That's for two very simple reasons. The first reason is the universe has a finite age, at least since the Big Bang. For reasons that we'll talk about later, the time between now and the Big Bang is fairly well determined to be about 14 billion years. Our best guess right now is something like 13.7 billion years. But it's not a guess, it's something that the data are telling us is true. So 13.7 billion years old, but remember that light travels at a finite speed. 1 light year per year is the best way of thinking about what the speed of light is. So if light travels at a finite speed, and the universe has a finite age, light has only been able to travel a finite distance between now and the Big Bang. So even if the universe were infinite, even if it did go forever, we couldn't see all of it. We can only see a certain patch, the patch from which light can get to us in less than 14 billion years. So we don't know the size of the universe. It could be infinite or it could be finite, but we nevertheless talk about the universe expanding. So how does that make sense? If you don't know how big something is, how do you know it's expanding? What we know is the relative size of the universe. By this we really mean the relative distance between different things in the universe. So just take two galaxies, and we know that they're moving away from each other. So we can ask quantitatively, how many years will it be before the distance between these galaxies is 10% more? How many years will it be before the distance is twice what it was? And that answer to that question, how many years will it be before the distance grows by 10%, is the same for any two galaxies. In other words, because the distance to different galaxies is proportional to their velocity that we see, it doesn't matter which galaxy you pick, as long as you ask the question, how many years will it take for the distance to grow by a certain number, you will always get the same answer. So we can talk about the relative size of the universe. We can say the universe was half its current size. What that means is the distance between any two galaxies was then half of what it is today. That's a perfectly sensible concept. So cosmologists invent something called the scale factor to the universe. The scale factor is a number which we set by convention equal to 1 today. And what the scale factor is telling us is the relative size of the universe. So when the scale factor was 1/2, that means that all the galaxies in the universe were half their current distance. When the scale factor is 2, everything will be twice as far apart as it is now. So one of the major projects that you want to complete, if you consider yourself to be a cosmologist, is to understand what the scale factor was doing as a function of time. So this plot shows the basic idea of what the scale factor does in an expanding universe. Right now it's getting bigger. Galaxies are growing apart from each other. We say that the universe is expanding. If you trace it backwards, it is, number one, very much smaller. We can trace it all the way back to 0. We don't necessarily think that we know what happens at 0, so we call it the Big Bang. The Big Bang, it's important to emphasize, is not a crucial part of our understanding of cosmology. It's a label we give to the place where we don't know what's going on. We know very well what's going on 1 second after the Big Bang, so we talk about the Big Bang as if we understand it, but really it's just a marker for our ignorance. Nevertheless, 14 billion years ago, there was something going on that we call the Big Bang, and we understand that everything there was squeezed on top of everything else, and it was expanding. So we believe, as we'll talk about very soon, that the rate of expansion in the past was bigger than the rate of expansion is now. So when we draw this plot, it has a sharper slope in the past than it does today. One of the things we would like to understand about this plot is its exact form from the Big Bang to today and into the future. One of the most surprising results of cosmology in the last 10 years is that today the expansion rate of the universe is going up. The universe is not only expanding, but it's accelerating, and that is why we believe in dark energy. So if we want to understand this phenomenon of the expansion of the universe in the context of general relativity, we remember that what Einstein tells us is that it's stuff in the universe that leads to the curvature of space-time. So the first question we should ask is, what kind of stuff is there in the universe? And even before we answer that question, we need to know what kind of stuff could there possibly be? What are the different forms of matter or stuff that could possibly fill the universe before we actually even go out and look at the universe and ask what we actually see? So let's first think about the things with which we are most familiar: the Earth, the Sun, or the galaxy. These are collections of particles. The Earth is made of particles. We talked earlier about atoms. The Earth is made of atoms. The Sun is made of individual atomic nuclei and electrons moving around, but they're made of particles. And these particles are bound together. So the Earth is bound together under the gravitational field of all the stuff in the Earth, likewise for the Sun, likewise for the galaxy. The Milky Way galaxy is bound together by the mutual gravitational force of all the 100 billion stars in it. So the first crucial thing about the expansion of the universe is that bound systems do not expand. So if you have two galaxies in the universe, each galaxy is orbiting under its mutual gravitational force, the distance between those two galaxies is getting bigger, but the galaxy itself is not getting bigger. The Earth is not getting bigger, you are not getting bigger, or if you are getting bigger, it is not because of the expansion of the universe, it's because of those donuts. So the bound systems do not get stretched along with the universe. And this is sort of a subtle thing that people are initially reluctant to believe, but it really is true. And in fact, it's the only way that you could even make sense of the claim that the universe was expanding. If everything in the universe, including people and atoms, expanded along with space, that would be exactly the same as nothing expanding. We only measure the distances between two objects in terms of the size of something else. If the size of everything increases, your rulers get stretched, the number of meters in between you and some distant galaxy wouldn't be seen to change. When we say that space is expanding, what we mean is the number of atoms that it would take to stretch from you to a distant galaxy is getting bigger. That's because the atoms are fixed and the galaxies are moving away. Absolutely strictly speaking, there's an equally good way of thinking about this in which the distance between galaxies is constant and all of the atoms are shrinking. That's just a really silly way of thinking about it, so we don't do that. It's much more convenient to think of atoms and you and me and the sun and the galaxy as remaining fixed in size, and the space in between the galaxies is getting bigger. But while the universe is expanding, even though atoms or particles do not stretch along with it, they become more dilute. More and more space is coming into existence. So if we draw a really big box, one that contains many, many hundreds of galaxies, and we say, how many galaxies per volume of space are there, that number will be going down. Space is expanding. The number of galaxies is basically not changing. The number of atoms is certainly not changing. So the number of atoms per cubic megaparsec, or the number of atoms per cubic centimeter, is going down. So we say that things are diluting away as the universe expands. Now, matter, to a cosmologist, is any set of particles that are moving slowly compared to the speed of light. Matter are things that get their energy from their mass. So Einstein, among his other accomplishments, said E equals mc squared. The interpretation of that equation, E equals mc squared, is not really energy equals mass times the speed of light squared. You need to attach some extra words to that equation to make sense of it. E equals mc squared is telling us that the rest energy of an object, the energy it has when it's not moving, is its mass times the speed of light squared. That's the minimum amount of energy that something can possibly have, and it's a constant. The mass is not changing, the speed of light is not changing. So the reason I'm going through this is to emphasize that the energy per particle is not changing if the particle is moving slowly compared to the speed of light. That, to a cosmologist, is what we call matter. As opposed to matter, we have radiation. We could have photons or other particles that are moving at the speed of light. If you're moving at the speed of light, your mass is zero. Your energy is not coming from E equals mc squared if you're moving at the speed of light. It comes from the frequency at which you're vibrating. But that frequency is changing as the universe expands because of this redshift. The cosmological redshift takes short wavelength, high energy photons and stretches them into long wavelength, low energy photons. So for particles that are moving slowly, E equals mc squared, and E is a constant. The mass per particle is a constant, so the energy per particle is a constant. But for particles moving at the speed of light, the energy per particle decreases as the universe expands. Photons and other particles that cosmologists call radiation lose energy as they become older and older in the history of the universe. So that's the important difference to a cosmologist between matter and radiation, how the energy density changes. The number density of particles is just how many particles per cubic centimeter. So the energy density is how much energy per cubic centimeter. In a region that grows along with the universe, the number density is constant. You're not creating new particles. But in a fixed centimeter, a cubic centimeter of space, the energy density will go down. The number density will go down, particles become more dilute, and therefore the energy density goes down. But the important difference between matter and radiation is that the energy density in radiation goes down more quickly. In radiation, not only do the particles dilute away, becoming less and less per cubic centimeter, but every particle loses energy. So this picture shows us basically what is happening as the universe is expanding. This is not a fixed amount of space. I've drawn a box that is getting bigger as the universe expands. So the number of particles in the box is a constant. The number of photons in the box is a constant. But the density per cubic centimeter of both particles and photons is going down. The energy per cubic centimeter is going down, but the energy in photons, in radiation, is going down more quickly because every photon is losing energy. So why belabor this point? The point is that the total energy in all the universe, in radiation, goes down more quickly than the total energy in matter. So you expect that as the universe gets older and older, matter will eventually win. There will eventually be more energy density in matter than in radiation, because the radiation has an energy that is going away more quickly. Contrary-wise, in the past, the energy density of matter is less important than the energy density of radiation. In the past, when all the photons were squeezed together with shorter wavelengths and higher energies, it was the photons that were winning. The photons were dominating. So a cosmologist will say that in the past, the universe was radiation dominated. It was the radiation that was important for the expansion of the universe. After that, it became matter dominated. So if you didn't know anything about the universe, if you didn't look out at the universe and discover the dark energy, if you pretended you were a cosmologist or an astronomer from 20 years ago, you would say that the things that could possibly be in the universe are either matter or radiation. It seems like those are the only possibilities. Particles that are moving slowly compared to the speed of light, and particles that are moving fast compared to the speed of light, that is to say, at the speed of light or only slightly less. Then what we want to do is put that idea to work. Understand in the context of general relativity how matter and radiation create the curvature of space-time. So in general, if you weren't in a simple context like the expanding universe, the concept of the curvature of space-time can be arbitrarily complicated. Space can be curved in all sorts of different ways. Just imagine a simple two-dimensional sheet of paper. Imagine all the different ways you can crumple it and bend it and twist it. A four-dimensional space-time can be crumpled and bent and twisted in correspondingly many more ways. So space-time curvature can be very complicated. But luckily for us, the universe is a simple place. So for the next couple lectures, what we're going to be doing is ignoring the fact that there are lumps in the universe. Well, for this lecture anyway, we'll be ignoring that there are lumps. We'll be approximating the universe as perfectly smooth, imagining that all over the place you have exactly the same density of stuff. Then, in that very nice circumstance, the curvature of space-time becomes very simple. There are only two different forms which the curvature of space-time can take. One is the expansion of space itself. The very fact that space is getting bigger adds a component to the curvature of space-time. One way in which space-time can be curved is that space gets bigger as a function of time. That's one way. The other way is that even without expansion, space can be curved all by itself. So forgetting about the fact that the universe is getting bigger, just looking at the universe at one instant of time, you have a three-dimensional space, and you can say, is that three-dimensional space flat or is it curved? What kind of curvature does it have? And there are different possibilities. So let's start with that possibility. Let's start with the curvature of space before adding in the expansion of the universe. So now we get to forget about time. We get to think about three-dimensional space and ask, is it flat or is it curved? So what does that mean? A flat geometry to space means that Euclid was right. Our good old high school geometry that you get by drawing things on this tabletop, which is perfectly flat, has certain rules. For example, if you draw a triangle in space, you add up the angles, the three angles inside the triangle, there's a rule that says you will get 180 degrees every time. That is actually not a hard and fast law of nature. That is a feature of a particular kind of geometry, which we call flat. It turns out to be true on this tabletop, but if you're a geometer, if you're professional, you imagine other possibilities. For a long time, people tried to prove that it needed to be the case, that the angles inside a triangle would have to add up to 180. Eventually they gave up because they realized it wasn't true that it had to add up to 180. There were other possibilities. So we can imagine that space itself is curved. The good news is that space is the same everywhere. So the curvature of space is just a number. It's a number that changes as a function of time, but right now we're looking at the universe at one moment in time, and we say space is either positively curved, negatively curved, or zero curvature, that is to say flat. There's only three possibilities. So this picture shows you those three possibilities. These three possibilities are demonstrating the operational difference between space being flat, positively curved, and negatively curved. If you're in a positively curved space, you draw a big triangle. It's like drawing a triangle on the surface of a sphere. And you can do that at home. You can add up those angles inside. Every triangle you draw on the surface of a sphere will have the property that the angles inside add up to greater than 180 degrees. The precise number of degrees they add up to will depend on the size of the triangle you draw. In a limit, when you go to a very tiny triangle, you'll come close to 180. As the triangles become bigger and bigger, it'll get bigger and bigger angles inside. So you could do that. You could do that to the universe and ask what its curvature was. You could even get that the angles inside added up to a number less than 180 degrees. In that case, we would call it negative curvature. And instead of living on the surface of a sphere, it would be like living on the surface of a saddle, something that bent in different directions in different regions. So this is something that we can go out there and test. The first person to actually think about these possibilities in a systematic way was Carl Gauss, a 19th century mathematician, and in fact he went out there and tested it. He drew a big triangle in the mountains near Hanover, and he measured the angles inside. He got 180 degrees up to his experimental error. It's an interesting thought experiment to ask if he had better precision instruments, would he have invented general relativity? Probably not is the answer, but he was a smart cookie, so you never know. So that is the possible scenarios for the curvature of space. Space could be flat. Euclid could be right. Space could be positively curved, like the surface of a sphere, or space could be negatively curved, like the surface of a saddle. The curvature of space is one of the two contributions to the curvature of space-time in a smooth expanding universe. The other contribution is just the expansion of the universe. So Einstein says that the curvature of space-time is being driven by the stuff that is in the universe. In other words, there should be some equation that relates the stuff that is in the universe to the curvature of space-time, in other words, the curvature of space and the expansion rate of space. So that equation was in fact derived from Einstein's equation by Alexander Friedmann, who was a Russian cosmologist. He derived this equation, which is the most important equation in cosmology, in 1922. Remember that relativity was only invented, general relativity, in 1915, and there was something else going on at the time called World War I, when general relativity was put together. But soon thereafter, Friedmann, who served in World War I, looked at what general relativity had to say about the expansion of the universe, and he came up with an equation. Sadly, he died in 1925 of typhoid, and it wasn't until 1929 that Edwin Hubble found that the universe is in fact expanding. So here is Friedmann's equation, the most important equation in cosmology. It's what tells us how the expansion of the universe responds to the stuff inside the universe. On the left-hand side, you have again some constants, some numbers, 8, pi, g, and 3. G is Newton's constant of gravity, familiar from Isaac Newton. Rho, is the Greek letter rho, is the energy density, the amount of energy in every cubic centimeter of space. It's going to change as the universe expands, but in this approximation where everything is very smooth, it's the same number from place to place all over the universe. So rho, the number of ergs per cubic centimeter, the amount of energy in every little part of the universe, is what drives the curvature of space and time in this way of thinking about things. So, on the right-hand side of the equation, you get two contributions to the curvature of space-time. The first contribution comes from the expansion. The second one comes from the curvature of space. So the expansion of the universe, remember, is measured by the Hubble parameter. Hubble was the one who told us that the number h is the constant of proportionality between the velocity of a distant galaxy and the distance to it. So the bigger h is, the faster the universe is expanding. So the particular way that h enters the curvature of space-time is in the form h squared. I don't have any simple, fun explanation for why it's h squared rather than h cubed. It turns out to be the Hubble parameter squared that is a feature of the curvature of space-time. And to that we have added k, the curvature of space itself. So the Friedmann equation is telling us that if you know the energy density, the number of ergs per cubic centimeter in the universe, and you know the Hubble constant, the rate at which the universe is expanding, then you can predict the curvature of space. Or you could do it in any other combination. If you knew the energy density and the curvature of space, you could predict the Hubble constant. Or best of all, if you could separately measure the Hubble constant and the curvature of space, then you would know what the energy density is going to have to be. This is going to be a crucial ingredient when later on we're going to say that dark matter and dark energy are really 95% of everything that there is. You can say that if ordinary matter is 5% of the universe, and by looking at gravitational fields we find new stuff, we find dark matter, 25%, dark energy, 70%, how do you know there's not something else that is even more, much, much more than there is dark matter and dark energy? This equation provides the answer to that. If you can separately measure the Hubble constant and the curvature of space, you know the total energy density of the universe. You're not leaving anything out. This is a manifestation of the usefulness of general relativity. Everything gives rise to a gravitational field. Everything makes space-time curved. So if you can measure the curvature of space and time, you've found everything. So what we're going to be claiming later on in the lectures is that we have measured the Hubble constant and we have measured the curvature of space, so we do know the energy density. We know how much stuff there is in the universe. And when we add up ordinary matter, and dark energy, we reach that number. There is no room for any more stuff in the universe that we haven't yet found. There could be 1% more here or there. There could be trace things that we don't know, but most of the universe we claim we understand what it is. So that's an important accomplishment. More specifically, what you like to do as a working cosmologist, it's nice to think that you have everything. What you want to do is to take this equation, you want to solve it. So remember, what we want to do is to plot out the scale factor as a function of time. In other words, what was the size of the universe at different epochs in cosmological history? So this is the equation that tells us that. If we not only know the value of rho, the value of the energy density, how many ergs are there in every cubic centimeter of space, not only do we know the value of the Hubble parameter and the value of the curvature of space, but if we know how the energy density changes as the universe expands, then we can solve this equation uniquely for the scale factor throughout the history of the universe. I can tell you, if you give me what the energy density is and how it changes, a unique history for how close together things were in the universe as a function of time. So at different points later on in the lectures, we'll be saying things like, when the universe was 1/1000th its current size, which is 400,000 years after the Big Bang. How do I know when the universe was a certain size, what time it was in the age of the universe? This is how I know. I plug into this equation and it tells me how big the universe is as a function of how old the universe is, which is the crucial question for cosmology. So this is the game that we're going to play for the rest of these sets of lectures. We're going to determine what is in the universe. What is the universe made of? Ordinary matter, and dark energy will be the answers. Remember, in the past, the universe was radiation dominated. Radiation today is very unimportant, so we even have to keep careful track of the radiation in today's universe because it used to be important in the past. Then we will use this equation, the Friedmann equation, to extrapolate from our current conditions back to the earliest times in the history of the universe. With that extrapolation, we will make predictions. And then we will test these predictions against stuff we observe today. It is never the case in this whole procedure that we say things like, well, it was Einstein who came up with this equation, it must be right. We're always trying to test these ideas. So we have an equation, it seems to work pretty well. How well do we test it? How well do we have empirical data that says this equation must be right? So as we will see in a few lectures, we can trace this equation, the Friedmann equation, back to when the universe was only a few seconds old after the Big Bang. We can use that extrapolation to make predictions about what the universe looks like right now. Those predictions will turn out to be true. This equation, the Friedmann equation, and Einstein's equation on which it is based, are, at least to a very, very good approximation, telling us something true about how the universe behaves. In lectures to come, we'll put that truth to use to see how the universe has evolved. We now have under our belts a picture of the entire universe that is a pretty good one. And it's a pretty impressive fact that we have such a picture. 100 years ago, we knew almost nothing correct about what the universe is like on very large scales, and now we have a picture that fits the data quite well. So the parts of it that we've talked about are basically the fact that when you look into the sky, you see that it's filled with galaxies. So the universe is big. By a galaxy, we mean some collection of stars moving under their mutual gravitational attraction, maybe 100 billion stars per galaxy. There's perhaps 100 billion galaxies spread throughout the observable universe, and they're all moving away from all the other ones. So the universe is getting bigger as a function of time. A crucial fact about this distribution of galaxies through space is that it's more or less uniform. The universe is smooth on very large scales, and this is an incredibly helpful feature as far as cosmologists are concerned, because that means that we can approximate the universe as being absolutely smooth. And that's exactly what we did. We looked at what Einstein said about space and time, and how space and time are joined together in one thing called space-time. That's the theory of special relativity. And that theory of that space-time has a dynamics. Space and time can expand, they can have a geometry, they can change with time, and that's the theory of general relativity. So if you have a universe that is perfectly smooth, that looks the same everywhere, then what you can do is plug that into general relativity and ask, how does a perfectly smooth universe change as a function of time? How does it expand? Where did it come from? Where will it go? We did that, and we derived an equation, the Friedmann equation, which relates the energy density in the universe to the way that space is curved and to the way that space is expanding. In today's lecture, we're going to go a little bit beyond that. We have a picture here from the Sloan Digital Sky Survey of how galaxies are distributed in our local region of the universe. And we said that, look, they look pretty smooth, and that's a very good approximation, and that was very helpful. Today, we will admit and take seriously the fact that they're not completely smooth. There is, in fact, structure there. Some of these galaxies are clumped together in groups of galaxies, in clusters of galaxies, even in things that are larger than clusters of galaxies, walls and sheets and filaments that stretch across the observable universe. At first glance, as cosmologists, we say that's kind of annoying, that the galaxies are not perfectly smooth, because we can really solve a lot of problems in terms of writing down equations and writing down what the solutions are, if everything were perfectly smooth. But on the other hand, it's certainly good news that there are local structures in the universe. It's good that the density is not absolutely constant throughout space. I am much more dense than the air that is around me, and that air is much more dense than the space in between the stars. So there's structure in the universe, and today we're actually going to take advantage of that structure. We're going to use it to weigh the universe, to find out how much stuff there is in the universe, in particular, how much matter there is in the universe. Of course, we've already given away the punchline. What we're going to find is that there's a lot of matter in the universe. There's more matter in the universe than we seem to be able to account for with ordinary matter, with atoms, with hydrogen and helium, and the other elements that we're familiar with from the periodic table. So today we won't get quite that far. What we're going to do is give you evidence that there's a lot of mass in the universe, much more than we see directly, but it will take future lectures to actually show that we're pretty sure that the mass that we don't see is some absolutely new kind of particle. So let's think about the process by which the universe went from being very smooth to having structures in it, to having galaxies and clusters of galaxies. This is an image which is an iconic image in cosmology. This is a picture of the cosmic microwave background. The cosmic microwave background, or the CMB, is the leftover radiation from the Big Bang. When the universe was less than about 400,000 years old, it was opaque. It was hot and dense and giving off light, but the light didn't get that far, it just kept bumping into free electrons. Once the universe was older than 400,000 years, it became transparent and the light streamed across the universe unimpeded, and that gives us the image we see right here. This is a snapshot of what the universe looked like when it was about 400,000 years after the Big Bang. Now it's about 14 billion years after the Big Bang, so a lot of time has happened, and we can see the effects of that passage of time. In this picture, what is actually shown are the slight differences in temperature from place to place in the cosmic microwave background. The blue spots are a little colder, the yellow and red spots are a little bit hotter, but only very, very slightly. The amount of variation in temperature in the cosmic microwave background is only about 1 part in 100,000. So what that means is that there were slight variations in the density of stuff back at that time. The density of the universe from place to place, 400,000 years after the Big Bang, was nearly perfectly smooth, but not exactly so. You might have had 100,000 particles in this region of space, then 100,001 in this region of space, and 99,999 in that region of space. Tiny variations over an ultimately very smooth distribution. So in lecture 11 in the future, we're going to talk in great detail about what kinds of patterns we see in the cosmic microwave background, how they got there, and what we learned from them. Today, let's just mention that the universe was a lot more smooth back then than it is today. Today, we see galaxies in some places, no galaxies in other places. There's a huge amount of contrast between the density in a galaxy and the density outside. So what happened from the microwave background era to today is gravity. Gravity worked on these tiny perturbations, these tiny ripples in the density of space, to increase their magnitude. Gravity works as a contrast knob. You turn up the contrast in the universe. You take dense regions and they become more dense, underdense regions and they become more underdense. They become less dense. What happens in that region where there's 100,001 particles, the force due to gravity is a little bit more than in that region where there's only 100,000. So this region with one extra particle pulls things toward it. And then it gets 2 extra particles. And then it has a little bit more mass, so it can pull even more things to it. This is a very slight effect. It takes literally billions of years to happen. But due to this effect, we go from an almost perfectly smooth distribution to a distribution which is still smooth on very large scales, but on small scales you have stars and planets and galaxies. So that happened over the last 14 billion years. Gravity turned up the contrast knob on the universe, and it did so in a hierarchical fashion. What that means is, on smaller scales, things can happen more quickly. It takes less time to build up a density region in some very tiny region of the universe than it does over megaparsecs. Over millions of light years across, it takes at least millions of years. Over billions of light years across, it would take at least billions of years. So the universe forms in a bottom-up way. You first form planet-sized things and star-sized things, then galaxy-sized things, clusters of galaxies, and larger structures. So it's no surprise that we see more structure on small scales than we do on large scales in the universe. We mentioned before that when you actually go and look out into the sky, what you see are a collection of galaxies. So here again is the Hubble Deep Field. This is an image of a randomly selected part of the sky. There's not anything special or especially interesting in that region, but the universe is more or less the same everywhere, so it doesn't matter. You take a picture of a region of the sky, and what you see is it is filled with galaxies. One of the things you notice about these galaxies are that they're very pretty. They are beautiful, they're aesthetically pleasing, and personally I've always wondered why that is the case. I'm not really sure why we find galaxies beautiful. It's hard to imagine some explanation for this from evolutionary psychology. A million years ago, when we were hunters and gatherers, we didn't know what galaxies were looking like. So it's hard to imagine some pressure that we would look at the galaxies sometime in the future and find that they are beautiful, but they certainly are. The other thing is that the galaxies look different. If you look at the different galaxies, some of them are red, some are blue, some of them are smooth, some of them are irregular. Partly this is because we're looking at galaxies at different moments of time. When you look at the sky, because the speed of light is finite, 1 light year per year, you're looking backwards in time. If you see a galaxy that is 1 billion light years away, you're seeing it as it looked 1 billion years ago. So it's not surprising in some sense that the galaxies look different. We're taking snapshots of them at different stages in their evolution. But on the other hand, even today, even the nearby galaxies that are all the same age do look different. Galaxies have a slightly individualistic character. So that's going to be important once we get to talking about what we can learn by studying individual galaxies. So what we're caring about for this course, dark matter and dark energy, is how to weigh the galaxies. How do we know how much stuff there is in a galaxy? Well, the simplest thing to do is just to look and to count. To say, well, if you know there's 100 billion stars, and you know that the average mass of a star is something like the mass of the sun, you're going to guess that it's about 100 billion solar masses worth of stuff in a typical galaxy. But it's always possible, even 100 years ago, people recognized that there was stuff in galaxies that we couldn't see directly. So you want a better way to get a handle on the total mass of the galaxy. How do you do that, of course? The answer is given to you again by gravity. Einstein showed that gravity is universal. Everything that exists in nature, everything that has energy, will give rise to a gravitational field. So even though you don't see it directly, you can tell how much stuff there is in a galaxy by measuring its gravitational field. The more mass that there is in the galaxy, the stronger the gravitational field will be. Now, in fact, we don't really need Einstein to tell us this. Isaac Newton could have told us this. Einstein invented a theory of gravity that is better than Newton's theory of gravity. It can describe things that Newton's theory can't describe. The expansion of the universe is not something that makes sense in Newtonian gravity. For Isaac Newton, space and time were fixed and absolute structures. He couldn't have talked about the Big Bang as some actual expansion of the universe itself. However, Isaac Newton could have talked very easily about a galaxy. A galaxy is in a regime, in a part of the universe, where Newton's theory of gravity is an excellent approximation to what is really going on according to Einstein. So we can think about Newtonian gravity. We can think about the fundamental law of Newtonian gravity, which is the inverse square law. If you have two objects, according to Isaac Newton, they exert a force on each other. That force is proportional to their mass. The heavier they are, the bigger the force is. It's also inversely proportional to their distance apart squared. So as the things get further and further apart, the gravitational force between them gets less and less. What that means is that if one object is orbiting around another one, when the orbiting object goes further and further away, it needs to orbit more and more slowly in order to perform a circle or an ellipse around the thing that it is orbiting. So in the solar system, this is perfectly clear. Mercury is moving around the sun very, very quickly because it's the closest planet. The Earth is moving at some medium speed, and Pluto is moving very, very slowly. It's not just that it takes Pluto longer because it has longer to go. It is actually moving more slowly around the sun because the force due to gravity is much weaker out there where Pluto is. This is, in fact, how we measure the mass of the sun. We don't know, we can't put the sun on a scale and weigh it. What we can do is look at the velocity with which planets are orbiting around the sun and measure its gravitational field. From measuring its gravitational field, we know what the mass is. So let's do the same thing with a galaxy. Let's measure the velocity of things moving around a galaxy. Here is a picture of the Andromeda galaxy. what we would want to do is to look at stuff that is on the outskirts of the galaxy. The difference between a galaxy and the sun is that the galaxy is not all concentrated in one small region. It's clear where the sun is, and outside the sun there's not a lot of mass. But a galaxy is spread out. It's much more diffuse. So you want to look at objects that are as far away as possible because they will be testing the accumulated gravitational field from everything that they are orbiting. If you want to make sure you're getting all the mass, you want to go as far away as possible. And the prediction from Isaac Newton would be that the further you go away, the slower things are revolving around the galaxy. If you measure the speed with which they're rotating, you can figure out the mass. So this project was undertaken in the 1970s by Vera Rubin, who's an astronomer at the Carnegie Institute of Washington. She measured what are called rotation curves of galaxies. So she looked at gas and dust moving around a galaxy, orbiting around it, and in fact, these optical images, these pictures that are taken with visible light, only show you part of the galaxy, the biggest part, the most massive part. But there's also, if you use radio telescopes, stuff that you can see, little wisps of gas and dust far outside. So you can use those as tests for what the gravitational field is. What Rubin found is that even though she looked at gas further and further outside the visible galaxy, the velocity of the orbiting gas did not decrease. As you went further and further out, the stuff keeps orbiting at the same velocity, more or less. The simple interpretation of that is, as you go further and further out, you're feeling the effects of more and more stuff. You have not succeeded in getting outside the entire galaxy. There's still stuff inside. However, we looked at gas that is far outside anything we can visibly observe in the galaxy. So the conclusion from Vera Rubin's observations of the rotation curves of galaxies is that there is stuff creating gravity in galaxies that we don't directly see. Stuff that is distributed in a much bigger, puffier halo, we call it, around the galaxy. So if Rubin is right, and current cosmologists think that she certainly is, the galaxy that we see is a decoration. It's a lit up little thing inside a much bigger structure, a halo made of dark matter. So if you plug in the numbers, what you find, according to Rubin's calculations, is that most of the stuff in the galaxy, most of the mass, most of the grams, or most of the ergs, is actually in dark matter. It's not in the visible matter. There's certainly also the possibility that we don't understand gravity, that Isaac Newton's theory does not apply in this regime. That would be a big surprise, and we'll talk about limits on that later, but for right now the simplest explanation is that there really is dark matter there. But that's a surprising result. That's the first evidence that we have that dark matter is an important part of galactic dynamics, so we would like to check that. Whenever you get a result that is that important, that it says there's a whole new kind of stuff out there in the universe, you don't just accept it and move on. You want to find more evidence that there's something like that going on or that contradicts it. So what you can do is look at clusters of galaxies. So what Rubin did was measure the rotation curves around individual galaxies. Individual galaxies have good features and bad features for this purpose. The good features are that galaxies are very organized. They're very regular. It's clear that there is a disk. It's clear that you're looking at stuff that is outside the visible matter. You can see what you are doing, basically. Clusters are a little bit messier. Clusters are generally not in disks. They're in spherical shapes. They're a little bit disorganized, and you might not be able to measure as cleanly what is going on. You have to be a little bit more clever about the techniques you use to weigh the total amount of stuff in the cluster. Here is a picture of a cluster of galaxies. What you see are, in the picture, at least dozens of different galaxies. In fact, a typical cluster will often have hundreds of galaxies in it. The good part about clusters of galaxies, even though they're a little bit messy, is that they have a good chance to be a fair sample of the universe. The worry when you look at an individual galaxy is that individual galaxies are all different. Some galaxies are small and ratty, some are big and very, very smooth. Clusters are all big enough that over the lifetime of the universe, there isn't time for different kinds of stuff to be segregated. Within a cluster, you basically are getting a fair sample of every kind of thing in the universe. The analogy that astronomers sometimes use is you're trying to measure the density of people in the United States in different places. But the data you have are not the total density of people. What you have is the membership directory for the American Astronomical Society. And it's broken down by city. So you can see, for example, there's a giant metropolis called Pasadena, California, and there's a tiny suburb called Los Angeles, California. There's a lot more astronomers in Pasadena, California, because Caltech is there and the Jet Propulsion Laboratory is there, than there is in Los Angeles. But the problem is, the reason you reach this untrue conclusion is because you didn't use a fair sample of the universe. Astronomers do not completely accurately trace the population at large. They are a biased sample. So the good thing about clusters of galaxies is that they are not a biased sample. You get a big enough chunk of the universe that what you see should be representative of what is actually going on. So the next picture that you can see is a computer simulation. It is not a photograph using data. It is the result of a computer trying to figure out how we went from early universe, almost smooth cosmology, to the late universe where you see these structures lighting up. And the good news is the computer simulations do a very good job at matching the data, so we can understand in our computers where different types of matter might be. An interesting thing about these galaxies are they're helping us to answer the question, where is the ordinary matter in galaxies? It might be that there's dark matter, and we're going to say that there is, but even without dark matter, you can still say, just because you see a galaxy and it's lit up, it's shining with stars, that doesn't mean that that's where the ordinary stuff is. What if there's just gas in between the galaxies? How do you know? Again, clusters provide the way to answer that question because they are a fair sample of the universe. What happens in a cluster of galaxies is that the gas in between the galaxies is pulled into the center of the cluster because of the force of gravity. And so even if that gas is dark, even if it is not shining and forming stars, even if in the desolate cold of intergalactic space it would be completely invisible, in the cluster where it clumps together, it heats up. The gas bumps into other gas and it goes to a very, very high temperature. It starts emitting X-rays. Here is an image from the Rosat satellite, a picture of a cluster of galaxies taken in X-rays. And what you see is that it's a much smoother distribution than you would see if you just took a photograph using visible light of this cluster of galaxies. What you see is that in between the galaxies that we thought we were observing, there's a lot of stuff there. What this is the hot X-ray gas in between the galaxies. And you can run the numbers. You can say how many hydrogen atoms, for example, are in the hot gas in between the galaxies versus the hydrogen atoms that are actually in the galaxies shining in the form of stars. The answer is there's more mass in between the galaxies in ordinary matter, just in hydrogen atoms, than there is in the stars in the galaxies themselves. About 2/3 of the total amount of ordinary matter in a cluster of galaxies is in between the galaxies themselves. So because we believe that clusters of galaxies are a fair sample of the universe, what that's telling us is, when we were weighing individual galaxies, we were missing a lot of ordinary matter. Forget about the dark matter. We didn't even get a fair sample of the ordinary matter because most galaxies are not in clusters. Most galaxies are out by themselves, and we can measure the galaxy, but we had no way of knowing what the total amount of invisible hydrogen was. In a cluster of galaxies, we can find it. It's lit up because it is heated up, and it's now emitting X-rays. So we can find out where the stuff is in a cluster of galaxies. There is a complementary way of doing it. Not only can we look at X-rays that are being emitted by the hot X-ray gas, what we can do is look at the shadow that the cluster of galaxies casts on the cosmic microwave background. The microwave background, remember, is coming from way in the past, from when the universe was only 400,000 years old. If a microwave from the CMB passes through a cluster of galaxies, it will scatter off of that hot gas. So when we look at the cluster, what we see is a dark spot. We don't see the microwave background here because it's been scattered by the hot gas. That is another way, besides using the X-rays, to measure the amount of stuff, and we get a consistent answer. What we find is that 2/3 of the ordinary matter in a cluster of galaxies is not in the galaxies themselves. Okay, so that tells us where the ordinary matter is. But what about this dark matter stuff? Should we weigh the clusters of galaxies and get the same answer? Well, it turns out there are two different ways to weigh the clusters of galaxies. One is to sort of do the analogous thing to what Rubin did with rotation curves. Unfortunately, clusters of galaxies are not aligned in this nice little disk, so you can't get a very simple rotation curve. But what you can do is measure the individual velocity of every single galaxy. There's a theorem in conventional classical Newtonian physics that the average velocity of all the different galaxies moving around is related to the total mass inside. The more mass you have, the faster they will be moving. That is the analogous statement to the fact that the more mass you have in a galaxy, the faster something will be orbiting. So this was first looked at actually in the 1930s, very, very long ago, by Fritz Zwicky, who was a Caltech astronomer at the time. He looked at the Coma cluster of galaxies. He measured their individual velocities, he plugged in the numbers, and he said, look, there's no way to explain these numbers on the basis of the matter we see. There must be matter there that we don't see. He wasn't absolutely taken seriously at the time. It was sort of too early. He was on the spot before people were ready for it. People figured, well, there's just stuff we don't see. There's hydrogen or whatever, ordinary stars and planets that we haven't taken into account. Someday we will find them. Today, of course, we can do better. We can take account of the stars and planets, and we don't find enough. The other thing to do is to look at the temperature profiles of the hot gas to find out what the temperature is of the gas starting from the center of the galaxy and moving our way out. Not only does this tell us how much gas there is, but it tells us the total gravitational field of the cluster of galaxies. And the total gravitational field depends on the total amount of mass. The answer, once again, is completely consistent, namely that even though there's a lot more matter in hot X-ray gas in between the galaxies than in the galaxies themselves, it is still not nearly enough to count for the total amount of matter in the cluster of galaxies, either by the dynamics of the galaxies zooming around or by measuring the total amount of gravitational field using the X-ray profile of the cluster. We get the same answer, which is that the total amount of mass is something like 5 times what we actually have in ordinary matter. This seems to be very good evidence that there needs to be something new in there, something that we call dark matter. This kind of argument doesn't completely rule out that it's not some very sneakily hidden form of ordinary matter, but it's pointing in that direction. So what can we learn from that? Is it possible that we're missing something? Is it possible that there is some dark form of ordinary matter that we haven't seen? It is certainly possible just from what we've said so far. In later lectures, what we're going to do is to put an absolute upper limit on the total amount of ordinary matter in the universe. The way that we're going to do that is to go back to the very early universe, to when it was 1 minute old or a few 100,000 years old, look at the relics that we get from the early universe in the form of helium, lithium, and other light elements, and also in the form of the cosmic background radiation. It turns out that properties of these relics from the early universe depend on the total amount of ordinary matter in the universe in a very specific way. And back then, ordinary matter was not separated into stars, gas, dust, planets. It was all absolutely smoothly distributed. So for once and for all, we can get a measurement of the total amount of ordinary matter. What we find is that it will be very consistent with what we think is there from what we see, from hot gas in clusters of galaxies and elsewhere. In other words, we have more or less a rigorous argument that the matter that we know must be there from the dynamics of clusters of galaxies cannot be ordinary matter hidden in some clever way. It has to be something new. So let me tell you about a way of thinking about what this answer is. I keep talking about the fact that the total amount of dark matter is about 5 times as much as the total amount of ordinary matter. But what units is that in? How should we think about this? Well, remember the Friedmann equation is the equation we use to govern the expansion of the universe. It relates the total energy density on average in the universe to the expansion rate and to the curvature of space. In other words, if you know the energy density and the expansion rate, the Hubble constant, then you can tell me what the curvature of space is right from the Friedmann equation. In yet other words, there is one particular value of the energy density which for any given value of the expansion rate will mean that the universe must be flat. In other words, there's a critical value of the energy density that says if I measure the Hubble constant and I know that the actual energy density is equal to that critical value, I know that the spatial geometry of the universe must be Euclidean. The spatial geometry must be flat. There must be no curvature. That's not to say that we necessarily have that critical density, but that is a density that we can define using the Friedmann equation. So this is very convenient for astronomers. They will measure the density that we see in units of how much density you would need to make the universe flat, the so-called critical density. It turns out that the ordinary matter that we see in the universe, what we will eventually show is limited very strongly by Big Bang nucleosynthesis and the microwave background, and what right now we're inferring from the matter that we actually see is about 5% of the critical density. Ordinary hydrogen atoms and other forms of stuff in the periodic table makes up about 5% of what you would need to make the universe spatially flat. So the other stuff in the universe, the dark matter that we see evidence for in clusters of galaxies, then makes up about 25% of the critical density. It's about 5 times as much as the ordinary matter. So that's a very interesting result, because 5% plus 25% is 30%. We see in matter, both ordinary and dark, about 30% of what you need to make the universe spatially flat, about 30% of the critical density. The reason why that's an interesting number is 30% is close to 100%, but it's not equal to 100%. So this number could have been anything. It could have been 1/billionth of 1%, or it could have been several trillion percent. It could have been any number, but it's 30%. It's pretty close to being 100%. That makes us suspicious. So 10 or 20 years ago, if you were talking to most cosmologists, they would have said, I bet that we just haven't found all the matter yet. I bet that once we go and do better surveys of the universe, we'll bring that 30% all the way up to 100%. It would be much more aesthetically pleasing if we had exactly the critical density than if we had only 30% of it. In the back of their minds was one other fact, which is that 30% is a number that is not a constant. It changes with time as the universe expands. So the energy density changes in time in a very specific way in a matter-dominated universe, but the critical density also changes, and they change with respect to each other. So if the critical density that we need, if we only have 30% today of the critical density, in the past we had a much closer value to the critical density. Things were very close to being spatially flat. So if we really lived in a universe that By now you're convinced, beyond any plausible doubt, that there is something called dark matter in the universe. What we've done is we've looked at the dynamics of bound systems moving under their mutual gravitational field. We've looked at galaxies, the rotation curves of stuff moving outside galaxies, and we've looked at clusters of galaxies, large samples of hundreds of galaxies, and thought about both what the galaxies are doing and what the hot X-ray gas in between the galaxies are doing. And what we find, either way, is that you can't explain the motions that you see unless there's more matter in the universe than the stuff we can directly observe. So this should be evidence that closes your mind about whether or not there is dark matter in the universe. Except that, of course, as scientists, we don't like to close our minds until we really are as sure as we can possibly be. So in this lecture, what we're going to do is just to convince you again. We're going to give you a completely independent set of information that points to exactly the same conclusion, that in galaxies and clusters, there's much more matter there than the matter that we actually see. What we did when we looked at the motions of galaxies and clusters is really we were mapping out the gravitational field of those objects. So Einstein told us that whenever you have stuff in the universe, it creates a gravitational field. So we have a surefire way of finding everything there is. Just map out the gravitational field, use that to work backwards, figure out how much stuff there is in the universe. So we did that, but we like to do the same thing in a different way. We took advantage of the fact that particles, whether these particles are really individual particles or entire galaxies, move in a very determined way in the presence of a gravitational field. But they're not the only things that are affected by gravity. Even light itself is affected by gravity. That's part of the conclusion that Einstein was able to draw from the fact that gravity is the curvature of space-time itself. Nothing escapes gravity's influence, so even a beam of light passing through a gravitational field will be deflected. This process of deflecting light due to gravity is called gravitational lensing, and we can use it as a completely independent way to figure out how much stuff there is in the universe. So the basic idea is simple. You take an object, the object gives rise to a gravitational field, and you pass a beam of light past that object. What's going to happen is the attractive force of gravity will bend the light ray as it passes by. In an extreme example, it can bend it quite a bit. So here is an artist's impression of a gravitational lens that might be formed by a galaxy where the thing being lensed is a quasar. A quasar is a very bright nucleus of a galaxy, the center part of a very young galaxy very far away, giving off a lot of light. So they look like points to us, just like stars do. So quasars come from the words quasi-stellar objects, because originally they looked like stars. Now we know that they're actually galaxy-sized things in the very early universe. So you look at a quasar far away, and you look in many, many quasars, and you get lucky enough to find an example where there's a quasar far away, and in between you and the quasar is a galaxy, or a cluster of galaxies, or something like that. If the gravitational field of the thing that is in between you and the quasar is sufficiently strong, you can actually deflect the light from that quasar on both sides of the lensing object and get multiple images, 2 images of the quasar. So this is something that people have been looking for a long time, and in the 70s and then in the 80s, they began actually finding them. So you can find pictures of things that look like exactly the same astrophysical object very, very far away, and it's because there's something in between that is breaking up the image into multiple copies. You might ask, how do we know that these 2 images that look the same are really of the same object in the background? The answer is, of course, we can take their redshifts. We can find out how far away they are. If you find 2 objects that look the same, they're right next to each other, maybe there's a little fuzzy thing in between, and you measure their redshifts and they're equally far away, it's very likely that what you're doing is looking at exactly the same object. In fact, you can do more than that. You can be more precise, looking at the spectrum of light from that object, and you can really verify that they are 2 different copies of the same thing. So the reason why it's called lensing is because it's exactly the same kind of thing that you would get when light passes through a piece of glass that is not absolutely uniform. If you have a piece of glass that is warped, has different shapes, then the image that you see of something behind it will be distorted when you see it. You can do that correctly to make a lens that focuses on you or defocuses, but when you see any arbitrarily warped piece of glass, it will always give you distorted looking images. It's the same kind of thing, except instead of a piece of glass, we are now looking through a distorted space-time, distorted by the stuff in between us and the stuff we're looking at. This idea of gravitational lensing, of light being deflected as it passes through a gravitational field, goes back to Einstein himself. While Einstein was working on Einstein's equation, when he was trying to derive the general theory of relativity, he was already thinking ahead. He was mostly coming up with the theory in his mind through thought experiments, but he was already thinking ahead to how will we know whether this theory is right? How will we test it against the data? Of course, we already had a theory of gravity from Sir Isaac Newton, which was really good. Everyone thought it was the best theory ever invented. And now Einstein is coming along with a different theory. There was already one piece of information that people knew about even before general relativity, which is that the motion of the planet Mercury around the sun was not quite right. It was not quite moving in the orbit that you would have predicted according to Newton's law of gravity. So what do you do when something moves in an orbit which is not quite what is predicted by Newton's law of gravity? You invent dark matter. And that's in fact exactly what was done. A French astronomer named Leverrier invented an invisible planet that was supposed to be existing between the orbit of Mercury and the orbit of the Sun. He called it Vulcan, and unsurprisingly, it was discovered several times. Every time it was discovered by mistake because it's not actually there. The idea was that this new planet was a mass that was distorting the motion of Mercury. It turns out not to be right. It turns out that it was in fact gravity that was behaving differently. And when Einstein invented general relativity, one of the first things he did was to test what the orbit of Mercury should be like in his theory, and he found that it agreed. This was, in Einstein's own words, the happiest moment of his life, when he realized that his new theory fit this already existing data. But he was also a good enough scientist to realize that it wasn't good enough to fit already existing data. You needed to make predictions for data that hadn't been taken yet. So as soon as Einstein invented general relativity, he realized that the fact that everything is affected by gravity means that even light will be affected by gravity. And this is something that Newton's theory didn't say anything about. So he was making a precise prediction that would be different in general relativity versus Newtonian gravity. However, the problem with this prediction was it was very tiny. the gravitational field from a star or from a galaxy, Einstein didn't know about galaxies at the time, he was thinking about stars or perhaps the sun. The sun is the closest thing to us that is a large, massive object, but still the gravitational field of the sun in absolute terms is just not that much. The amount of deflection that you get by light by the sun is a very, very tiny angle. And there's a more profound problem when you're trying to use the sun as a gravitational lens, which is that the sun is bright. So if the sun is sitting there and you're looking close by the sun, hoping that it will lens some object through its gravitational field, the problem is you can't see any other objects, you just see the bright blue sky behind you. There is one loophole to this problem, of course, which is the possibility of a total solar eclipse. If you're lucky enough to be in the right place at the right time when the moon goes in front of the sun, then the sun is there, still gravitationally lensing things behind it, still deflecting the light of stars that are nearby, but suddenly you're not blinded by the sun itself. So if you take a picture of some stars in the sky and then wait until a future moment when the sun is in front of them and there is a total eclipse, and then you take a picture of those stars again, you can compare the image of those stars, their positions on the sky, with the sun there and without the sun there. If general relativity is correct, the gravitational lensing effect of the sun will distort the positions of those stars in your image on the sky. So fortunately for Einstein, he invented general relativity in 1915, and there was the perfect eclipse that was going to happen in 1919. Now, of course, 1915, most people in the world, when you ask what was going on in 1915, if they're physicists, they will say Einstein was inventing general relativity. Most other people will say World War I was going on. So World War I ended a couple of years after Einstein completed relativity, and the eclipse came up in 1919. An expedition was launched to make observations of this eclipse by Sir Arthur Eddington, who was a British astrophysicist and a very respected scientist in his own right. So Eddington launched an expedition, went and took images of the stars in the sky before and after the sun was there, and he compared them. When he got back to England, they developed the film, and they realized that, in fact, yes, there was gravitational lensing of these stars. There was deflection of light by the sun, exactly as Einstein had predicted. So what you had was a theoretical construction by a famous German scientist being verified by an observation done by a famous British scientist, and it was actually taken at the time to be a very nice example of international cooperation among scientists. Even though these countries were on different sides during World War I, they still agree that space-time is curved, which is a good thing to agree on. It also was the thing that launched Einstein's celebrity. Back in 1905, when Einstein was inventing special relativity, he wrote many papers that made him famous in the scientific community. Everyone in 1915 appreciated the genius of the general theory of relativity, but in 1919, when Eddington showed that the sun was deflecting light, just as Einstein had predicted, it made the front page of the New York Times. The general public suddenly realized that Isaac Newton had been superseded as the leading person to understand how the universe works, and Einstein took on that mantle. That was when he really became a public figure and often used his public persona to good purposes. These days, we go beyond looking at just the gravitational lensing of the sun. We use gravitational lensing as a tool to weigh things. So the foremost thing that we're going to use it to weigh are, of course, clusters of galaxies that we believe are fair samples of what is in the universe. There is another use that I will mention just parenthetically. We'll get to it in more detail in later lectures, but that is to look for individual dark stars. If you have a dark star, some form of thing that is about the size of the sun, when I say about, I mean anywhere from 100 times the mass of the sun to 1/100th or 1/1,000,000th the mass of the sun, you can find those using their gravitational lensing effect because they move through the sky. So they're dark, but they're moving through the sky, and every once in a while they will pass in front of a visible star. You can see the effect of the gravitational lensing on that visible star. It's very tiny, and it's called microlensing. That's a way to find dark stars within our galaxy, and that's something that we're going to be talking about later when we're talking about what might the dark matter possibly be. For right now, we're trying to establish that dark matter really does exist, so we're going to use gravitational lensing to weigh clusters of galaxies. In other words, to map out the gravitational field of a cluster of galaxies in some detail. You can see, if you think about it, there is an obstacle to doing this that is not there for the sun or for these dark stars that you might find by microlensing. The obstacle is that the cluster of galaxies is not moving in the sky. Both the cluster and whatever is behind it are sitting there on cosmological timescales. So even if you see something being lensed behind it, what you want to do is to find out how much lensing there is, but you don't know ahead of time where the object was. If the lens was not there, where would you see it in the sky? You can't compare before and after images because nothing is moving. The universe is more or less static over these very, very large distances. So what you're trying to do is to figure out a way to measure how much deflection of light you really have, even though you can't first put the lens there and then move it. You just have to deal with the fact that it's there. Well, there's actually two different techniques that people have worked out to use to measure how much deflection of light there is. The first one was implicit in the first example we showed, the fact if you have strong gravitational lensing, if the lensing is so strong that you see more than one image of the background object, then you can figure out the angle by which it is lensed. If you have one object in the background, it passes through a cluster of galaxies and you see two images of it, then there's an angle on the sky that is telling you what is the angle by which the light is being deflected. That is called strong gravitational lensing and leads to some very pretty pictures that you can see how strong the lensing is of some background galaxies. The other possibility is weak gravitational lensing, and weak gravitational lensing is actually much more common than strong lensing. Strong lensing, you're very lucky to find such a good example. But weak gravitational lensing is just the idea if you have a cluster of galaxies, you have a bunch of galaxies in the background, they will all be distorted by just a little bit. If you only had one galaxy in the background that passed through the gravitational lens, you wouldn't know what it was supposed to look like and where it was supposed to be, so it wouldn't help you in figuring out how much lensing was going on. But if you have many galaxies in the background, their images will be distorted in a systematic way by the gravitational field of the cluster. So the fact that they begin to line up, not due to any intrinsic alignments, but because of how the light has passed through the clusters of galaxies, is going to be able to tell you how much lensing there was. And so both of these techniques are in fact going to be used. Here is another image of a cluster of galaxies. You can see a couple of visible galaxies in the middle, and then also up and to the right, there is a bright red object in this picture. This is an ancient star-forming region. It's an intrinsically interesting object all by itself. Forgetting about dark matter, just thinking about astrophysics. This is some proto-galaxy that is coming to life, bursting with new stars and giving off a lot of radiation. It is in the background of this cluster of galaxies. We can measure its redshift, we can find that it's far away, and you see that it's distorted a little bit. You can see that it's aligned in a certain way that is sort of circularly wrapping around the cluster of galaxies. So let me show you this animation. This is an animation of how NASA scientists have been able to reconstruct the image of that star-forming region is distorted by the fact that it passes by the cluster of galaxies. So what you see is an initial image giving off radiation. The light from that image passes by the cluster of galaxies, and as it is passing by, it is warped, and it goes from a fairly square image at the beginning to one in which it is distorted into this little ellipse. Here is another image. This is a reconstruction, once again, of what would happen if we were able to violate all the laws of physics, move faster than the speed of light, and travel from us here on Earth back to that star-forming region, going by the cluster of galaxies. What you see at the first is the cluster of galaxies with the star-forming region in the background. It's distorted into a little ellipse. And as you zoom past the cluster, what you see revealed is the original shape of the star-forming region, which was actually closer to a rectangular shape than to this ellipse. So you see that the effect of the cluster of galaxies acting as a gravitational lens is to change the shape of the background star-forming region. If you have enough examples of that, you can reconstruct how much gravity there was in the cluster. So here is a more typical example of what you actually see with data. Here is a cluster of galaxies once again. We've already seen this picture, but now we want to look closely at this picture. In particular, we want to look at the tiny galaxies on the outskirts of this cluster. Many of these galaxies are not in the cluster themselves, they are in the background. They're behind the cluster, and their light is passing next to it on their way to us. So what you see if you look at the galaxies in the background is there's a systematic alignment. You see circles. There are regions of galaxies that are all little arcs, and these arcs all wrap around the original cluster. That is the distorting effect of the gravitational lensing caused by the heavy gravitational field of all the mass in the cluster. You can see the number of arcs, you can see the amount by which they're distorted. If there were only one of them there, it might just be that that galaxy looked like an arc all by itself. But if there are many, many of them, there shouldn't be any reason why galaxies are lining up in little arcs, especially if they are at different redshifts themselves. The reason why we see these little arcs is because of the lensing effect of the cluster. And we know enough to take that data, the number of arcs and their distortions on the sky, and reconstruct from it the total gravitational field of the cluster of galaxies. So you will not be surprised to hear the answer, I hope, which is that the total amount of mass you need to explain the amount of gravitational lensing is 5 times as much as the amount of ordinary matter in this cluster of galaxies. In other words, the total mass that we've reconstructed by dynamical mechanisms, looking at moving galaxies and moving gas, is in correspondence with the total amount of mass that is implied by gravitational lensing observations. So this is nice. This is telling us that we're on the right track. If we didn't get that answer, it would have been very interesting. What if you had weighed these clusters of galaxies using 2 very different methods, but you're trying to measure the same quantity, and you'd gotten a different answer? That would mean that you didn't understand something. You didn't understand either something about clusters of galaxies, or you didn't understand something about gravity or general relativity or something like that. The fact that the 2 methods agree and give us the same answer for the masses of these clusters of galaxies seems to imply that we are on the right track. You can never be 100% sure that you are on the right track. It is always possible that you're being tricked one way or another. What happens is, as you collect more data, get more examples of what is going on, the chances that you are being tricked get smaller and smaller. At some point, it becomes a waste of your time to contemplate that you are being tricked, and you should just say, well, now I have found something. There are enough independent things pointing to the existence of dark matter in clusters of galaxies that we've reached the point where either we should say that the dark matter really does exist, or something even more profound is going on, something with gravity itself. So let me look at one pretty picture and then one profound example. Both of these are hot off the presses new results in cosmology. The pretty picture is a 3-dimensional map of the dark matter distribution in one direction of the sky. This is from the Cosmos survey undertaken by NASA, and basically what they did is they said, let's take every telescope we have in all the different wavelengths of the electromagnetic spectrum and point them at the same region of the sky. So they took images with the Hubble Space Telescope, they took images in X-rays, they took infrared images, radio telescopes, ultraviolet images, and they tried to reconstruct not just the picture of the sky in one direction, but the entire 3-dimensional distribution of stuff. They have both the redshifts to different objects and the images at each redshift. So what they can do from that is reconstruct where the dark matter is. And it's a little bit of a rough reconstruction. It's not highly precise, but you see the answer in this picture. There's a distribution of dark matter throughout space. The distribution more or less matches where we see the ordinary matter. It matches it more than well enough that we can say we're on the right track. What we think is where the dark matter is where it should be. On the other hand, it doesn't match it perfectly. So right now, one of the hot topics in research on things like this is asking, are the things that we see, which indicate that there is dark matter in a place where there is not a bunch of ordinary matter, an indication of some novel mechanism in the evolution of galaxies and clusters that removes ordinary matter from dark matter, or is it just that the data are not very good yet? This is a kind of thing where we really don't know the answer to that yet. We're at the point where we do have a belief, a strong belief that there is something called dark matter, but the detailed dynamics of the dark matter and how it evolves along with the ordinary matter is something we don't yet fully understand. There's a lot more work to be done in that direction. Now let me show you, this is my favorite example. This is something called the bullet cluster of galaxies. And it's a sequence of images of the same object using different techniques. So the first image is just a picture from the Hubble Space Telescope of this bullet cluster. And if you stare at it long enough, and you're a professional observational cosmologist, you look at this picture and you go, aha, that is actually two clusters of galaxies. There's a large concentration of galaxies on the left-hand side of the picture. On the right-hand side, a little bit up, there's a slightly smaller concentration of galaxies. So you can actually take the redshifts of these galaxies and you can show they really are associated with each other. They are gravitationally bound. These are not just a chance superposition of galaxies at different distances. So this is an interesting example of a double cluster of galaxies. There are two more or less independent objects, but they're at the same redshift. They're right next to each other, cosmologically speaking. So remember, we said that when we just think about ordinary matter in clusters of galaxies, forgetting for the moment about dark matter, in a cluster of galaxies, even the ordinary matter is mostly in between the galaxies. It's mostly in the form of hot X-ray gas that is not concentrated in the galaxies themselves. Something like 2/3 or 3/4 of the ordinary matter is in this hot gas. So when you see a cluster like this, especially one with an interesting shape, it's fun to take a picture of that cluster in X-rays and see where most of the ordinary matter is. So the next image shows us in pink an X-ray image of the bullet cluster, a picture of where the ordinary matter is. The ordinary matter is glowing in X-rays, and what you see is actually quite remarkable. The place where the ordinary matter is, shining in X-rays, is displaced from where the galaxies are. The ordinary matter is also coming in two clumps, just like the galaxies are, but it's in between the two clusters of visible galaxies. Somehow, the location of where the ordinary matter is, where most of the hydrogen and hot gas in this cluster is not in the same location as where the galaxies are. So this is interesting, but it is not a complete mystery. There's a very simple explanation for how this could come to be. The explanation is that in the recent cosmological past, these two clusters of galaxies collided and they went right through each other. You have to think sort of separately about the dynamics of the individual galaxies and the dynamics of the hot gas in between. The galaxies are fairly sparsely spread through the cluster. If you take the total area that you see in a galaxy, it's only a tiny fraction of the size of the cluster as a whole. So when these two clusters went right through each other, came out the other side, the individual galaxies didn't even notice. The individual galaxies just went from one side and came out the other one. You started with two groups, and you ended up with two groups, perfectly separate. However, the hot X-ray gas inside these clusters of galaxies does notice the hot X-ray gas inside the other one. So when these two groups come together, these two clusters, and collide, there is a shock front set up in the hot X-ray gas. The gas is slowed down from moving by the fact that it is interacting with the gas in the other cluster. So what you see is basically the gas gets stuck in between, and you get a separation between where the galaxies are and where the gas is in between. That is, of course, intrinsically interesting to astronomers. Astronomers would like to understand how clusters have evolved in cosmological history. You don't get many examples of two clusters of galaxies passing through each other, so it's a lot of fun just to think about that. But also, from our point of view, we're interested in dark matter and dark energy. This provides a unique opportunity to ask, what does the dark matter behave like? If we believe that there really is dark matter in these clusters of galaxies, one of the features of dark matter is that it doesn't interact very much. The fact that it doesn't interact very much is most obviously displayed by the fact that the dark matter is dark. Most of the interactions over cosmological length scales in things in the universe are either through gravity, which affects everything, or through electricity and magnetism, which affects charged particles. So even atoms, which are neutral, are made of charged particles. That's why we can see them. Dark matter is not charged, otherwise it would be easy to see. They would not be dark. So the dark matter, to a very good approximation, is collisionless. Dark matter particles go right through each other. They do not bump into each other. That's the reason why in an individual galaxy, the dark matter halo is some big puffy thing. The bright visible stars have condensed and settled into the middle of this halo because ordinary matter can bump into other ordinary matter, cool off, and settle down to the middle. Dark matter falls into a galaxy and just passes right through. The dark matter ends up in a big puffy cloud where the ordinary matter settles into the middle. So what we want to know is, where is the dark matter in the bullet cluster? We started with two separate clusters. Both of them had ordinary matter and dark matter. They passed through. The hot gas got stuck in the middle. What did the dark matter do? So the next image is a reconstruction based on data of where the dark matter is in the bullet cluster. In particular, it's a reconstruction of where the gravitational field is in the bullet cluster based on gravitational lensing observations in the background. What you see is quite remarkable. The dark matter, or at least the gravitational field in the bullet cluster, is centered on where the galaxies are. But remember, the galaxies are not centered on where most of the mass is. Most of the mass is in the hot gas in between the galaxies, and it was displaced. But the gravitational field stuck along with the galaxies. So if you look at the next picture, we've superimposed where the gravity is and where the matter is. The gravity is in blue, the matter is in pink, the matter is giving off these hot X-rays. We see a very clear example of where the gravitational field in this cosmological object is pointing in a different direction than where most of the matter is, most of the ordinary matter. That can't be explained if you don't believe in dark matter. If you only believed in ordinary matter, the stuff that is causing the gravity is the ordinary matter. So the stuff where the gravitational field is should be where the ordinary matter is. In fact, this is not only good evidence that there is dark matter in the sense that there's a lot more stuff there than what we see, it's also good evidence that we're on the right track when it comes to gravity. Up until now, we could always have believed that the reason why the gravitational field in an individual galaxy or in a cluster of galaxies is stronger than it should be is because we didn't quite understand how gravity was working on